In the summer of 2025, a small telescope in the Chilean desert recorded a faint smudge moving across the sky. Within hours, the trajectory had been calculated. Within days, the conclusion was unavoidable. The object was not from here. It had come from somewhere else. And as more telescopes turned to look at it, the questions began to multiply faster than the answers. What follows is the full story of the object now called 3I/Atlas. What it is, what it might be, and why a respected Harvard astronomer published a paper arguing that the most reasonable interpretation of what we are seeing is that the object was made by something. If the quiet, careful exploration of an open question is the kind of thing you came here for, consider hitting that like button and subscribing. It genuinely helps more than you know. Now, let's begin. The solar system is, in most respects, a closed environment. The sun holds the planets in their orbits through gravity, the planets hold their moons, and a great cloud of icy debris called the Oort cloud surrounds the entire arrangement at a distance of perhaps 1 light-year, a vast, sparse halo that marks, in some functional sense, the outer boundary of the gravitational territory the sun controls. Everything within that boundary is bound to the sun. Everything outside it belongs to other stars, other systems, or to the empty space between them. Material has been flowing between stars for as long as stars have existed. The galaxy is full of debris, comets ejected from young planetary systems by gravitational encounters with giant planets, fragments knocked loose from collisions between rocky bodies, dust grains drifting outward from supernova. The amount of this material is enormous in absolute terms. The space between stars is so large that the density is, by ordinary standards, almost unimaginably low. A cubic kilometre of interstellar space contains, on average, fewer than 1 particle of any significant size. But the volume of interstellar space is so vast that the total mass of debris exceeds, by a substantial margin, the total mass of all the planets, moons, asteroids and comets in any single planetary system. Some of this debris occasionally enters another planetary system. The process is straightforward in principle. An object drifting through interstellar space travelling on a trajectory that happens to bring it close to a star will be deflected by that star's gravity. If the object's speed and angle are appropriate, it will pass through the inner regions of the system on a hyperbolic trajectory, an open curve that bends around the star without being captured by it, and then continue on into interstellar space on the other side. The encounter is usually brief, lasting months or at most a few years, and the object's path through the system is determined by physics that has been understood since Newton. The trajectory is predictable. The encounter is unremarkable in the sense that it is the natural consequence of well-understood gravitational dynamics. What is remarkable is that, until very recently, no such object had ever been observed entering our own solar system. The expected rate of interstellar object encounters had been calculated by various researchers over the decades, with estimates that ranged across orders of magnitude depending on the assumptions made about the population of objects drifting through interstellar space. The most reasonable estimates suggested that interstellar objects of sizes large enough to be detected by ground-based telescopes should pass through the inner solar system at rates ranging from perhaps 1 per decade to 1 per century. The actual rate, based on observations, had been 0 for as long as systematic searches had been conducted. The absence of detected objects was not necessarily inconsistent with the theoretical predictions. The predictions were uncertain, the detection methods were imperfect, and the population of objects might simply have been at the low end of the predicted range. But the absence persisted, and as decades passed without any clear detection, some researchers began to suspect that the theoretical estimates were wrong, and that interstellar objects might be substantially less common than had been predicted. Then, in October 2017, the first one was found. A second was discovered in 2019, a third in July 2025. The third object, called a 3I/Atlas, is the one we are concerned with here. Its arrival completed a transition in our understanding of the solar system that had been underway for less than a decade. Before 2017, no interstellar object had ever been confirmed. After 2025, 3 had been confirmed. The implications of this transition are still being worked out. What is certain is that the boundary between our solar system and the rest of the galaxy is, in practice, far more porous than we had imagined for most of the history of astronomy. Things come in, things go out. The recent discoveries are not flukes. They are the beginning of a new awareness of how connected our local environment actually is to the vast, otherwise distant volume of space beyond it. The change of perspective produced by these discoveries was, in some respects, a return to ideas that had been considered seriously by earlier generations of astronomers before being set aside for lack of evidence. The possibility that material from other planetary systems might occasionally arrive in our own had been discussed for decades. Specific predictions had been made about the rates at which such arrivals should occur. The absence of confirmed detections had not refuted these predictions, but it had made them seem less urgent, and the question of interstellar visitors had drifted toward the margins of astronomical concern. The discoveries of the last decade reversed this drift. Interstellar objects were no longer hypothetical. They were a recognized category of body with 3 confirmed members, and the study of that category had become a legitimate part of modern astronomical research. 3I/Atlas, as the third and most extensively studied of the confirmed objects, would play a central role in establishing what that study could be. The first 2 interstellar objects to be detected in our solar system, 1I/Oumuamua in 2017 and 2I/Borisov in 2019, established the basic categories that astronomers use to think about such objects. Oumuamua was strange. Borisov was almost normal. Between them, they framed the conceptual space into which any subsequent interstellar object would be expected to fit. 3I/Atlas, when it arrived in 2025, did not fit comfortably into either category. It shared features with both, contradicted features of each, and added features that had not been seen in either. The picture that emerged from the early observations was of an object that did not match the expected patterns, and that required astronomers to revise, almost from the moment of its detection, the framework they had developed for thinking about interstellar visitors. The most immediately striking feature of 3I/Atlas was its size. Oumuamua had been small. Estimates of its dimensions varied widely, but the longest axis was probably less than a few hundred meters. Borisov was larger, but still modest by the standards of solar system comets, with a nucleus estimated at perhaps half a kilometer across. 3I/Atlas, based on the initial observations, was substantially larger than either of its predecessors. Hubble Space Telescope measurements eventually constrained the nucleus to a size between approximately 440 meters and 5.6 kilometers, a range whose upper end made the object the largest interstellar visitor ever observed by a substantial margin. The implications of the larger size were not trivial. Larger objects produce more reflected light, allowing more detailed observation. They contain more material, providing more opportunity for spectroscopic analysis of their composition. They also raise statistical questions, because larger interstellar objects should be substantially less common than smaller ones, and the discovery of a large one early in the era of interstellar object detection suggested that the population of such objects might be larger or more easily detectable than the early theoretical estimates had assumed. The second striking feature was the speed. All 3 of the confirmed interstellar objects moved through the solar system on hyperbolic trajectories, open curves that bent around the Sun without being captured, but the specific speeds and trajectories differed. Oumuamua had moved at a velocity that was unusual, but not extraordinary by interstellar standards. Borisov had moved at a higher velocity but on a trajectory that took it relatively far from the Sun. 3I/Atlas moved faster than either, approaching the inner solar system at approximately 137,000 miles per hour relative to the Sun. The high velocity meant that the object's encounter with the inner solar system would be relatively brief, that it could not have been gravitationally captured by any of the planets it passed near, and that its origin point in interstellar space could be calculated with somewhat greater precision than for the slower previous visitors. The third feature was the timing of its activity. Comets in our own solar system typically begin to develop visible comas, clouds of gas and dust surrounding the nucleus, when they cross what is called the snow line, the distance from the Sun at which water ice begins to sublimate. The snow line for water in our solar system is at approximately 3 astronomical units, or about 3 times the distance from the Earth to the Sun. Inside that distance, water ice on a comet's surface vaporizes rapidly enough to produce the gas and dust cloud that defines a comet's appearance. Outside it, comets remain largely inert. 3I/Atlas, when first observed, was well outside the water snowline, and yet was already showing significant activity: gas emission, a developing coma, an apparent tail. The activity at that distance was unexpected and required explanations beyond simple water ice sublimation. The fourth feature was the chemical composition that began to be revealed by spectroscopic observations. The early measurements showed unusually high levels of carbon dioxide relative to water, an unusual ratio of certain isotopes, and a general chemical signature that did not match the typical composition of solar system comets. Some of these differences could be explained by the object having formed under different conditions than those that prevailed in the early solar system. Others were more difficult to explain. The chemical composition became, in subsequent months, one of the central topics of scientific interest in 3C/Atlas, with multiple research teams conducting detailed analyses of the available data and producing papers that explored the implications of the unusual chemistry. Taken together, these features made 3I/Atlas the most scientifically interesting interstellar object yet detected. It was larger, faster, and more chemically distinct than its predecessors. It behaved in ways that required new explanations. It became almost immediately the most intensively observed interstellar object in the history of astronomy, and the data accumulated about it would, in the months that followed, produce questions that the previous interstellar visitors had not raised. The distinction between an object that originated in our solar system and an object that came from somewhere else is, in practice, a question about orbital dynamics. Every object bound to the Sun moves on a closed orbit, an ellipse, in the simplest case with the Sun at one focus. The orbital period may be short, as for the inner planets, or long, as for objects in the outer solar system, but the orbit is closed, and the object returns to the same general region of space repeatedly over the course of its existence. An object that originated elsewhere and is merely passing through, by contrast, moves on an open trajectory, a hyperbola, in the case of an object moving fast enough to escape the Sun's gravity. The open trajectory does not return. The object passes through, bends around the Sun under the influence of gravity, and continues on into interstellar space on the other side. The mathematical distinction between these two trajectory types is captured by a single number, called the orbital eccentricity. For closed orbits, the eccentricity is less than 1. A perfectly circular orbit has eccentricity 0, while elongated elliptical orbits have eccentricities approaching 1 without ever reaching it. For open trajectories, the eccentricity is greater than 1. The transition between these two regimes is sharp and well defined. An object with eccentricity exactly 1 is on a parabolic trajectory, which represents the marginal case between bound and unbound motion. Below 1, bound; above 1, unbound. The specific value above 1 indicates how fast the object is moving relative to what would be required to merely escape the Sun's gravity. Higher eccentricities indicate higher speeds, with the speed at infinity being a function of the eccentricity and other orbital parameters. The eccentricity of 3/Atlas, as calculated from observations after its discovery, was approximately 6.3. This is an extraordinary value. For comparison, the most eccentric objects in our own solar system, long-period comets from the Oort cloud, have eccentricities very close to 1, occasionally slightly above it due to gravitational perturbations from passing stars or other influences. Genuinely interstellar objects have eccentricities that are clearly above 1, and the specific value depends on the object's velocity relative to the Sun. Oumuamua had an eccentricity of approximately 1.2, Borisov had an eccentricity of approximately 3.4. 3I/Atlas at 6.3 was substantially more eccentric than either, reflecting its substantially higher velocity. The implications of this extreme eccentricity were several. First, it confirmed beyond any reasonable doubt that the object had come from outside the solar system. No process operating within the solar system can produce such an orbit. The eccentricity is far too high to result from any plausible gravitational interaction with the Sun and planets. The object must have entered the solar system on a trajectory already characterized by the high relative velocity, which means it must have had a relative velocity with respect to the Sun, even when it was still far from the solar system's gravitational influence. Such velocities are characteristic of objects that have been moving freely through interstellar space for a long time, accumulating differences in motion relative to other nearby stars through the various perturbations that affect such motion. Second, the high eccentricity meant that the object's path through the inner solar system would be relatively brief and could be calculated with high precision. Bound objects on long elliptical orbits spend most of their time at great distances from the Sun, moving slowly. Unbound objects on hyperbolic trajectories pass quickly through the inner solar system and spend almost no time in the regions accessible to detailed observation. 3I/Atlas would be observable in the inner solar system for only a few months, from the time it became close enough for ground-based telescopes to detect through its perihelion passage near the Sun in February 2026, until it moved far enough beyond the orbit of Jupiter to be lost to most telescopes. The observation window was narrow, and astronomers had to compress the entire scientific study of the object into that window. Third, the calculated trajectory could be extrapolated backward in time to determine the approximate direction from which the object had come. The calculation could not identify a specific star of origin, because the object had been drifting through interstellar space for an unknown but very long period, and during that time it had been perturbed by gravitational interactions with various passing stars and with the general distribution of matter in the galaxy. But the calculation could identify the general region of the galaxy from which the object had emerged, and could constrain the range of possible source environments. The results of this calculation, when they were eventually completed and published, would suggest that 3I/Atlas had emerged from a region of the galaxy unlike the local neighbourhood of our own Sun, a region characterised by colder temperatures, older stars, and conditions different in important ways from those that produced our own solar system. The asteroid Terrestrial Impact Last Alert System, known by its acronym ATLAS, is a network of telescopes operated by the University of Hawaii and funded primarily by NASA. The system was designed to scan the sky systematically for objects that might pose impact hazards to Earth, particularly small asteroids onto trajectories that could bring them close to or directly toward the planet. The telescopes are not large by modern astronomical standards. Each has a primary mirror of approximately half a metre, but they are optimized for the specific task of surveying large areas of sky repeatedly, with high cadence and adequate sensitivity to detect moving objects against the static background of stars. The system operates 4 telescopes located in Hawaii, Chile, and South Africa, providing nearly continuous coverage of the night sky as the Earth rotates. On the night of July 1, 2025, the ATLAS telescope, located at the Rio Hurtado Observatory in northern Chile, was conducting its routine survey of the night sky. The observatory sits at an altitude of approximately 4,500 meters in the Atacama Desert, one of the driest and clearest locations on Earth for astronomical observation. The atmospheric conditions were typical for that location: clear skies, low humidity, minimal light pollution from any nearby populated area. The telescope was operating in its normal automated survey mode, taking sequential images of overlapping sky regions and comparing each image to previous observations to identify objects that had moved between exposures. The detection occurred during the processing of images from a region of sky toward the constellation Sagittarius. A faint object appeared in multiple images, moving against the background of fixed stars at a rate consistent with an object somewhere in or near the solar system. The motion was relatively slow at first, typical of an object still at substantial distance from Earth, but the position of the object relative to the Sun and the geometry of the observed motion allowed an initial estimate of its trajectory. The estimate, calculated automatically by the survey's data processing pipeline, indicated that the object was on an orbit unlike anything the system had previously detected. The automated alert was processed by the human operators of the ATLAS survey within hours of the initial detection. Additional observations were requested from other telescopes in the ATLAS network to confirm the detection and refine the trajectory calculation. By the time the next morning came in Chile, the object had been observed multiple times by multiple telescopes, and the trajectory calculation had been refined to the point where the conclusion was unmistakable. The object was on a hyperbolic orbit, eccentricity well above 1, and it was moving fast. It was, in other words, almost certainly interstellar in origin. The discovery was reported to the Minor Planet Center, the international clearinghouse for astronomical observations of small solar system bodies, on July 2, 2025. The Minor Planet Center is operated by the Smithsonian Astrophysical Observatory, under the authority of the International Astronomical Union, and it serves as the official body for assigning designations to newly discovered objects in the solar system. Upon receipt of the ATLAS observation data and verification of the discovery, the Minor Planet Center issued an electronic circular announcing the detection. The object was assigned the provisional designation C/2025N1, where the C indicated that it appeared to be a comet, the 2025 indicated the year of discovery, the N indicated the half-month in which the discovery occurred, and the 1 indicated that it was the first object discovered in that half-month. A subsequent designation, 3/Atlas, would be added later to formally identify the object as the third interstellar object on record. The initial public announcement of the discovery was modest. Astronomical discoveries are made constantly, and most receive little attention beyond the specialist astronomical community. The discovery of a possible interstellar object, however, was unusual enough to attract immediate attention from professional astronomers around the world. Within days of the announcement, telescopes from multiple countries had begun observing the object, refining its trajectory, and beginning the initial characterization that would occupy professional astronomy for the next several months. Within weeks, the first scientific papers had been posted to preprint servers, presenting initial measurements of the object's brightness, color, motion, and chemical signature. What is interesting about the discovery, from the perspective of the broader story, is how routine the underlying observation was. The Atlas system was conducting its standard survey. The object was detected through standard automated procedures. The trajectory was calculated by standard software. The discovery was reported through standard channels. Nothing about the process was unusual until the trajectory calculation produced its conclusion. From that point forward, everything would be unusual. The intensity of the observations, the scientific attention, the public discussion, the speculative interpretations. But the discovery itself was a product of routine astronomy operating in its normal mode, finding something extraordinary because the survey infrastructure had been designed over decades to be capable of finding exactly that kind of thing if it ever appeared. In the hours and days following the initial detection by the Atlas telescope, the trajectory of the newly discovered object was refined through additional observations from telescopes around the world. The process of trajectory refinement is fundamental to the study of any newly discovered solar system body. The position of the object at multiple times is used to fit a mathematical model of its motion under the gravitational influence of the Sun and the major planets. As more observations accumulate, the model becomes more precisely constrained, and the predicted future and past positions of the object become more accurate. For a typical solar system object, the trajectory refinement process is relatively quick. Within a few days of discovery, the orbit is usually well determined to the extent needed for further observations to be planned and conducted efficiently. For 3I/Atlas, the refinement process produced increasingly extraordinary results. Each additional observation tightened the constraints on the orbit and made the conclusion that the object was interstellar in origin more secure. The eccentricity, initially estimated at approximately 4 or 5, was refined upward as more observations were processed, eventually settling at approximately 6.3. This value placed the object well outside the range of any plausible bound orbit. No conceivable scenario involving gravitational dynamics within the solar system could produce such an orbit from an originally bound object. The conclusion was unavoidable. The object had come from outside. The trajectory refinement also revealed several features of the object's path through the solar system that became subjects of subsequent discussion. The first was the closest approach to the Sun, called the perihelion. The calculations indicated that 3I/Atlas would pass the Sun at a distance of approximately 126 million miles, which is slightly closer than the orbit of Earth and somewhat farther than the orbit of Venus. The perihelion passage was predicted to occur on approximately February 19, 2026, about 7 months after the initial detection. The perihelion distance was significant because objects pass through the most intense solar heating at perihelion, and the activity of comets typically peaks during this period. For 3I/Atlas, the perihelion would provide the best opportunity for detailed spectroscopic observation, since the heated nucleus would be sublimating substantial amounts of material and producing a bright coma visible for detailed analysis. The second feature revealed by the trajectory refinement was the path's relationship to the orbits of the major planets. The trajectory of 3I/Atlas passed relatively close to several planets during its transit through the inner solar system. The object would pass near Mars in October 2025, providing an opportunity for observations from spacecraft already in orbit around Mars. It would pass through the solar conjunction in late 2025, a period when the object would be on the opposite side of the Sun from Earth and therefore not observable from Earth-based telescopes. After emerging from solar conjunction in early 2026, it would pass relatively close to Earth at a distance of approximately 170 million miles in December 2025, close enough for detailed observations from Earth-based and Earth-orbiting telescopes. and it would pass relatively close to Jupiter in March 2026, providing another opportunity for observations from spacecraft. The third feature was the path's apparent origin direction in the sky. By extrapolating the trajectory backward, astronomers could determine the direction from which the object had been approaching the solar system before the Sun's gravity began to influence its motion. This direction, called the radiant, was located in the general region of the constellation Sagittarius, which corresponds to the direction of the galactic center. The radiant did not identify a specific star of origin. The object had been drifting through interstellar space for far too long for its origin star to be identifiable, but it did provide information about the general region of the galaxy from which the object had emerged. The fact that the radiant pointed toward the galactic center suggested that the object had originated in the inner regions of the galaxy, where stellar density is higher, and the conditions for planet formation are somewhat different from those in the local solar neighborhood. The fourth feature, which would not become fully apparent until later observations, was the extreme age suggested by the kinematic properties of the object. The high relative velocity of 3I/Atlas with respect to the Sun, combined with its trajectory direction, suggested that the object had been drifting through interstellar space for a very long time, possibly longer than the age of the solar system itself. The estimates that would eventually emerge from kinematic analyses suggested an age of approximately 8 billion years, compared to the 4.5 billion year age of the solar system. If the age estimate was correct, 3I/Atlas was significantly older than the Sun and its planets, having formed in some now vanished planetary system around a star that may have died long before our own Sun was born. Each of these features, as it emerged from the trajectory analysis, added to the picture of an object that was not merely interstellar, but extraordinarily ancient, having travelled through the galaxy for billions of years before finally crossing the path of the solar system in 2025. The confirmation that 3I/Atlas was a genuinely interstellar object rather than some unusual long-period comet from the Oort cloud depended on the precision with which its orbit could be determined. The eccentricity of an orbit is a calculated quantity, derived from the observed positions of the object over time, and the precision of the calculation depends on the number and quality of the observations. In the first days after the discovery, when only the initial Atlas observations were available, the eccentricity was constrained with substantial uncertainty. Values ranging from approximately 3 to 9 were consistent with the available data. As more observations from more telescopes accumulated over the following weeks, the uncertainty was reduced and the calculated eccentricity converged to approximately 6.3 with a precision of better than 0.1. The convergence of the eccentricity to a value well above 1 was the critical confirmation. Values near or slightly above 1 could conceivably result from gravitational perturbations within the solar system, particularly if the object had originated in the Oort cloud and been deflected by some unusual interaction. Values substantially above 1, 3 or higher, required an interstellar origin, because no process operating within the solar system could produce such high eccentricities from a previously bound object. The value of 6.3 was definitive. It placed the object in the same category as Oumuamua and 2I/Borisov, and it ruled out any reasonable alternative explanation involving solar system origin. The confirmation was further reinforced by the calculated value of what astronomers call the asymptotic velocity, or V infinity. This is the speed the object would have had relative to the Sun before it entered the influence of the Sun's gravity, essentially the speed of the object in interstellar space, before the encounter with our solar system began to affect its motion. For 3I/Atlas, the calculated V infinity was approximately 36 miles per second, which corresponds to approximately 130,000 miles per hour. This value is consistent with the typical velocities expected for interstellar objects relative to the local standard of rest, the average motion of stars in the solar neighborhood. The specific value of the V infinity is significant because it relates to the age and origin of the object. Objects that have been moving freely through interstellar space for very long times accumulate substantial random velocities through gravitational perturbations from passing stars, and their velocities tend to become randomized with respect to the motion of any particular star. Younger interstellar objects, which have not yet had time to accumulate such perturbations, tend to have velocities more closely matching the motion of the local standard of rest. The relatively high V infinity of 3I/Atlas, taken together with its trajectory direction, suggested that the object was old, old enough to have accumulated substantial random velocity through long-term gravitational perturbations. This was the initial indication of the extreme age that would later be confirmed by more detailed kinematic analysis. Subsequent calculations would suggest that the object had been wandering through the galaxy for at least several billion years, and probably much longer, before its trajectory happened to carry it through the inner solar system in 2025. The confirmation of the interstellar origin was sufficient to trigger the formal redesignation of the object. Under the conventions established by the International Astronomical Union, interstellar objects receive a special designation prefix, I, that distinguishes them from the comets and asteroids that are native to our own solar system. The Minor Planet Center, after reviewing the trajectory data and confirming the interstellar classification, issued the formal designation 3I/Atlas on July 2, 2025. The 3 indicated that this was the third interstellar object on record, after 1I/Oumuamua and 2I/Borisov. The I indicated the interstellar status. The Atlas indicated the survey that had made the discovery, following the standard astronomical convention of naming comets after their discoverer. The redesignation marked the moment when 3I/Atlas became formally and officially an interstellar visitor rather than merely an unusual comet. The transition was administrative rather than physical. The object itself was the same regardless of how it was designated, but the change in classification carried significant implications for how the object would be treated by the astronomical community. Interstellar objects are subjects of intense interest, and the formal classification opened the way for the kind of coordinated international observing campaign that the object's nature required. Within days of the redesignation, observing time on major telescopes around the world was being allocated to 3I/Atlas observations, scientific papers were being prepared for publication, and the public communication of the discovery was being managed by the various agencies and institutions involved. What had begun as a routine survey detection by a half-meter telescope in the Chilean desert had become, within a few days, the most important astronomical event of 2025. The third confirmed observation of an object that had originated in a different planetary system, in a different region of the galaxy, perhaps in a different epoch of the universe's history, now passing briefly through the small region of space where we happen to live. The naming conventions for astronomical objects are governed by a complex set of rules administered by the International Astronomical Union, the international body that serves as the authoritative arbiter of astronomical nomenclature. Different categories of object follow different naming rules. Comets are named after their discoverers, with additional designations indicating the year and order of discovery. Asteroids receive a provisional designation upon discovery and may eventually receive a proper name proposed by the discoverer and approved by a committee of the IAU. Planets, moons, and other categories follow their own specific rules. The conventions have evolved over centuries and represent an attempt to balance the historical practice of honouring discoverers, the practical need for unique identifiers, and the international cooperative nature of modern astronomy. For interstellar objects, the naming convention was established relatively recently, in response to the discovery of 1I/Oumuamua in 2017. Before that discovery, no formal convention for interstellar objects existed, because no interstellar objects had ever been confirmed. The IAU established the new convention specifically to handle the new category, and the convention was designed to be clear, simple, and easily extensible to additional objects as they were discovered. The format consists of a number indicating the order of discovery, 1 for the first, 2 for the second, and so on, followed by the letter I, indicating interstellar status, followed by a slash and either a proper name or the name of the discovering survey or individual. The first object, discovered by the Pan-STARRS survey in Hawaii in 2017, received the designation 1A/Oumuamua, with the proper name Oumuamua being a Hawaiian word meaning roughly scout or messenger from afar. The second object, discovered by Gennady Borisov in 2019, received the designation 2I/Borisov, using the discoverer's name in the position usually reserved for the survey name. For 3I/Atlas, the convention produced its automatic designation. The 3 indicated that it was the third object in the interstellar category. The I indicated interstellar status. The Atlas reflected the survey that had made the discovery. The full designation was straightforward and uncontroversial, following the established convention precisely. There was no proposal for a proper name in the manner of Oumuamua. the object's official designation reflected its origin in a survey discovery rather than in an individual observer's recognition, and the convention did not require a proper name to be assigned. The Minor Planet Center, the organization that administers the actual assignment of designations under IAU guidance, processed the designation through its standard procedures. The MPC had been tracking the new object since the initial Atlas report on July 1st, and the formal designation was published on July 2nd in a Minor Planet electronic circular distributed to the international astronomical community. The circular included the orbital elements that had been calculated from the available observations, the assigned designation, and the assignment of the object to the interstellar category. The publication of the circular constituted the official confirmation of the discovery and the formal entry of 3I/Atlas into the astronomical record. At the same time as the interstellar designation was being assigned, the object also received a parallel designation as a comet. Under the comet naming conventions, the object received the designation C/2025N1 Atlas, where the C indicated that it was a non-periodic comet, the 2025 indicated the year of discovery, the N1 indicated that it was the first comet discovered in the second half of July 2025, and the Atlas indicated the discovering survey. The dual designation reflected the object's status as both an interstellar object and a comet, categories that overlap but are not identical. Oumuamua had been designated as an interstellar asteroid rather than a comet because it showed no clear signs of cometary activity. 2OE/Borisov had been clearly a comet with substantial cometary activity. 3I/Atlas was similarly clearly a comet with the developing coma and tail that had been observed from the earliest detections. The naming process, while administratively routine, carried symbolic weight. By formally designating the object 3I/Atlas, the international astronomical community was acknowledging the arrival of another interstellar visitor and the importance of its study. The designation would become the identifier used in all scientific publications, observing proposals, public communications, and other materials related to the object. Decades from now, when the data accumulated about 3I/Atlas is analysed and reanalyzed by future generations of astronomers, the designation will continue to identify the specific object that passed through the inner solar system in the months around the perihelion of February 2026. The naming in this sense was the formal recognition that the object had become part of astronomical history, not merely a temporary phenomenon to be observed and forgotten, but a specific object whose properties would be studied indefinitely as part of the larger effort to understand the population of interstellar bodies and what they reveal about the broader structure of the galaxy. The third such object on record, the first that almost from the moment of its formal designation would produce more questions than answers about what it actually was. The story of 3I/Atlas cannot be fully told without first telling the story of 1I/Oumuamua, the first interstellar object ever confirmed in our solar system. The two objects are connected not by any direct physical relationship, they came from different regions of the galaxy and shared no common origin, but by the conceptual and observational legacy that Oumuamua left behind. The questions raised by Oumuamua were the questions that astronomers had in mind when 3I/Atlas was discovered. The explanations that had been proposed for Oumuamua's anomalies were the explanations that astronomers reached for first when 3I/Atlas's own anomalies began to be characterized. Whatever we conclude about 3I/Atlas, the conclusion will be shaped in part by what we did and did not conclude about Oumuamua before it. Oumuamua was discovered on October 19, 2017 by Robert Werrick, a postdoctoral researcher at the University of Hawaii, working with the Pan-STARRS 1 telescope on Haleakala. The discovery occurred about 40 days after the object had passed its closest approach to the Sun, meaning that Oumuamua was already on its outbound trajectory when it was first observed. The available observation window was short, only about 2.5 months of useful observations, after which the object became too faint and too distant for further study from Earth. Within that brief window, however, the object displayed a series of properties that did not match the standard categories of solar system bodies, and the explanations for those properties have remained subjects of active scientific debate. The first anomaly was the object's shape. Oumuamua's brightness varied dramatically as it rotated, suggesting that it was highly elongated, perhaps 10 times longer than it was wide. This is a far more extreme aspect ratio than any natural body in our solar system. The closest analogues are some asteroids that approach aspect ratios of 3 or 4 to 1, but 10 to 1 is essentially unprecedented in the population of bodies whose shapes have been measured. The unusual shape was the first indication that Oumuamua might be something other than a typical asteroid or comet. The second anomaly was the object's behaviour as it moved away from the Sun. Oumuamua showed no visible coma, no tail, no signs of the gas and dust emission that would identify it as a comet. By those criteria, it should have been classified as an asteroid, but it also showed a small but unmistakable non-gravitational acceleration, a slight extra push outward that could not be explained by gravitational forces alone. Such accelerations are common for comets, where they result from the rocket-like effect of gas being emitted from the comet's surface. But the absence of observed gas emission from Oumuamua made the standard cometary explanation difficult to maintain. Various alternative explanations were proposed: emission of material that happened to be invisible to the observing instruments, unusual radiation pressure effects, peculiarities of the object's internal structure, but none was fully satisfactory. The third anomaly was the object's apparent colour and reflectivity, which suggested a composition that did not match the typical compositions of asteroids or comets. Oumuamua appeared red in the spectroscopic measurements, which is consistent with various organic-rich surfaces, but its specific spectral characteristics did not exactly match any known class of small body. The reflectivity was higher than typical asteroids and lower than typical comets that have been resurfaced by recent activity. The combination of features did not fit cleanly into any standard category. In response to these various anomalies, the Harvard astronomer Avi Loeb proposed in 2018 that Oumuamua might be artificial, specifically that its properties were most economically explained as a thin, sail-like structure of artificial origin, perhaps the discarded technology of an extraterrestrial civilization. The proposal was controversial. The mainstream scientific response was generally skeptical, with most astronomers preferring the various natural explanations even when none of them fully accounted for all the observed properties. The debate produced a substantial volume of scientific literature, including papers proposing alternative natural explanations, particularly the suggestion that Oumuamua might have been a fragment of solid hydrogen ice, or a fragment of nitrogen ice from a Pluto-like object in another planetary system, both of which could provide non-gravitational acceleration through evaporation without producing visible gas emission. The Oumuamua debate established the framework within which subsequent interstellar objects would be evaluated. The standard cometary explanations available at the time of its discovery had been inadequate, and the search for better explanations had produced a rich literature exploring the various ways in which interstellar objects might differ from solar system bodies. When 3I/Atlas was discovered in 2025 with its own set of anomalies, the framework from the Oumuamua debate was already in place. The questions had been asked. The explanations had been proposed and debated. The new object would be evaluated against this background, and the patterns of the previous debate would be recapitulated in modified form in the discussions of the new object's properties. The second confirmed interstellar object, 2I/Borisov, served in important ways as a counterpoint to Oumuamua. Where Oumuamua had been strange in nearly every respect, its shape, its lack of visible cometary activity, its non-gravitational acceleration, its uncertain composition, Borisov was almost reassuringly normal. It looked like a comet. It behaved like a comet. It had the chemical signatures expected of a comet. The main thing that distinguished it from comets native to our own solar system was that its orbit clearly placed it on an interstellar trajectory. Apart from that fundamental fact, Borisov could easily have been mistaken for an unusually distant long-period comet of the type that occasionally arrives from the Oort cloud. The discovery of 2I/Borisov was made by Gennady Borisov, a Crimean amateur astronomer, on August 30th, 2019. Borisov was operating a telescope of his own construction at the Margot Observatory in Nauchny, in the Crimean Peninsula, and his discovery was made during a period of routine observation looking for comets. The discovery was confirmed within days by other observers, and the interstellar nature of the orbit was established within weeks. The Minor Planet Center assigned the designation 2I/Borisov in September of 2019, formally establishing it as the second interstellar object on record. The orbital eccentricity of 2I/Borisov was approximately 3.4, substantially above the threshold of 1 that distinguishes interstellar from bound orbits, but lower than what would later be measured for 3/Atlas. The trajectory took the object through the inner solar system on a path that brought it to perihelion in December 2019, at a distance of approximately 190 million miles from the Sun. Somewhat outside the orbit of Earth, but well inside the orbit of Mars, the object remained observable for substantially longer than Oumuamua had been, allowing for more detailed scientific study, and the observations that accumulated over the months of its visit produced one of the most thoroughly characterized cometary objects in astronomical history. What the observations revealed was that 2I/Borisov was, in essentially every respect except its interstellar origin, a typical comet. Its spectroscopic signatures showed the expected mixture of water, carbon monoxide and carbon dioxide, with proportions broadly similar to those found in comets native to our own solar system. Its dust production matched expectations. Its development of coma and tail as it approached the Sun followed standard cometary patterns. The nucleus, eventually estimated at approximately half a kilometre across, was a typical size for a small comet. The chemical and physical properties of the object placed it firmly within the population of cometary bodies that scientists understood reasonably well from observations of solar system comets. The implications of Borisov's normality were significant for the broader picture of interstellar objects. If the population of interstellar bodies were dominated by objects similar to Borisov, relatively ordinary comets that happened to be on interstellar trajectories, then the existence of such objects would not require any fundamental revision of our understanding of how comets form and evolve. Comets are ejected from planetary systems through gravitational interactions with giant planets, particularly during the early stages of planetary system formation, when the gas giants are still in the process of migrating to their final orbital positions. The ejected comets carry the chemical signatures of their original planetary systems with them, and once in interstellar space they drift indefinitely until, in rare cases, they happen to encounter another planetary system. Borisov's properties were consistent with this picture. It looked like a comet from somewhere else, but it looked like a comet. Oumuamua's anomalies had been so striking that they had raised questions about whether the population of interstellar objects might include things very different from anything in our own solar system. Borisov, by being so normal, suggested that the population probably did include many objects that were essentially like solar system comets, and that the unusual features of Oumuamua might have been peculiarities of one specific object rather than typical features of interstellar bodies in general. The expectation among many astronomers, after the Borisov observations were completed, was that future interstellar objects would probably also be relatively normal comets, with Oumuamua perhaps representing some unusual subcategory or rare outlier within a broader population of comet-like bodies. When 3I/Atlas was discovered 6 years after Borisov, this expectation was carried into the early analysis of the new object. Astronomers expected, at least initially, to find another comet that happened to be on an interstellar trajectory. The early observations were interpreted in this framework. As the data accumulated, however, the framework began to strain. 3I/Atlas shared important features with Borisov. It was clearly a comet with coma and tail and the standard spectral signatures of cometary activity, but it also exhibited features that did not fit the Borisov pattern. The object turned out to be different from Borisov in ways that mattered, and the differences would, over the months that followed its discovery, produce a body of scientific puzzles that the Borisov data had not prepared anyone to expect. The arrival of 3I/Atlas in 2025 produced an immediate statistical puzzle that became one of the central topics of discussion in the early scientific response to the discovery. The puzzle was simple to state. Before October 2017, no interstellar object had ever been confirmed in our solar system. Between October 2017 and July 2025, a period of less than 8 years, 3 had been confirmed. The rate of confirmed interstellar object detection had gone from 0 per century, sustained for all of recorded astronomical history, to approximately 3 per decade. This rate increase was extraordinarily large, and explaining it required some account of why interstellar objects had suddenly become detectable when they had not been detectable before. The most straightforward explanation involved the improvement of detection capabilities. The various sky surveys that operate today, Pan-STARRS, Atlas, the Zwicky Transient Facility and others, are substantially more capable than any survey systems that existed before approximately 2010. They cover larger areas of sky, with greater sensitivity, more frequent cadence, and better automated processing of the resulting data. The combination of these improvements meant that small, faint, fast-moving objects could be detected today that would have been entirely missed by any earlier generation of observation systems. The recent increase in interstellar object detection might therefore reflect the recent improvement in detection capabilities rather than any actual increase in the underlying population of objects passing through the solar system. This explanation, while plausible, did not fully account for the observed pattern. The detection capability improvement had been gradual over decades rather than concentrated in the years just before 2017. If improved detection had been the primary driver, the first detection should have occurred earlier, perhaps in the mid-2000s, with subsequent detections following at a relatively steady rate as capability continued to improve. The actual pattern was different. No detections at all for the entire period when modern surveys were operating, followed by 3 detections in close succession beginning in late 2017. The clustering of the 3 detections within an 8-year window, after decades of 0 detections by progressively more capable systems, suggested that something more than gradual capability improvement might be involved. An alternative explanation involved an actual increase in the rate of interstellar object passages through the inner solar system. If the underlying population were variable rather than constant, the recent cluster of detections might reflect a genuine fluctuation in the number of objects entering the solar system. Various scenarios could in principle produce such fluctuations. A nearby star whose proximity perturbed the orbits of objects in the local interstellar medium might temporarily increase the rate of interstellar object passages. A dispersing cloud of small bodies, the remnant of a planetary system disruption, might pass through the solar neighborhood. The local interstellar environment might simply be more variable than had been assumed, with periods of higher and lower interstellar object flux occurring naturally over time. A third explanation, less commonly discussed but worth considering, involved selection effects in the detection process itself. The 3 confirmed interstellar objects had all been detected during their relatively brief passages through the inner solar system, when they were close enough to the Sun and Earth to be observable by ground-based telescopes. The vast majority of interstellar objects passing through the outer solar system would never be detected, because they would remain too faint and too distant for the existing surveys to find. The actual rate of interstellar object passages through any defined volume of the outer solar system would be much higher than the rate of confirmed detections, perhaps by factors of hundreds or thousands. The recent detections might therefore represent a tiny biased sample of a much larger underlying population, and the apparent recent increase might be an artifact of how the detection process worked, rather than a feature of the underlying flux. Each of these explanations had some merit, and the actual situation probably involved a combination of all of them. What the explanations had in common was the implication that interstellar objects are substantially more common in the galaxy than had previously been suspected. The recent detections, whatever their specific cause, established that interstellar objects pass through the inner solar system at rates of at least once per few years, which means that the broader population in interstellar space must be very large indeed. Estimates derived from the recent detection rate suggested a population of perhaps 10 to the 25th to 10 to the 26th interstellar objects of sizes comparable to those that have been detected, a population so vast that it constitutes a significant fraction of the total mass of small bodies in the galaxy. This realization had implications beyond the specific objects that had been detected. It meant that the solar system is not as isolated from interstellar space as the previous absence of detections had implied. Material flows in and out. The objects that have been detected are a small biased sample of a much larger population that surrounds us at all times. The discoveries of 2017, 2019, and 2025 had transformed our understanding of the galactic environment in which the solar system exists. In the days and weeks following the discovery of 3I/Atlas, the question of the object's actual physical size became one of the first major puzzles in its characterization. The size of a celestial body is not directly observable from telescopic measurements at the distances involved. What is observed is the object's brightness, which depends on a combination of factors including the size of the object, its reflectivity, the geometry of the observation, and various other parameters. Converting from observed brightness to physical size requires assumptions about these other factors, and the assumptions can be more or less accurate depending on what is actually known about the object. For a newly discovered object whose properties are poorly understood, the size estimates can have substantial uncertainties. The earliest size estimates for 3I/Atlas, based on the initial brightness measurements from the Discovery observations, suggested that the object was relatively large by interstellar standards, substantially larger than either Oumuamua or 2I/Borisov. The exact size of estimates varied substantially, with some researchers suggesting diameters of several kilometers and others arguing for smaller sizes if the object's reflectivity was assumed to be unusually low. The discrepancies reflected the uncertainty in the reflectivity assumption, which is one of the most difficult parameters to constrain for newly discovered objects. A complicating factor for 3I/Atlas was the developing coma. When a comet has a substantial coma, a cloud of gas and dust surrounding the nucleus, the observed brightness includes light reflected from both the nucleus itself and from the dust in the coma. The two contributions can be difficult to separate, particularly when the coma is bright relative to the nucleus. For 3I/Atlas, the coma was substantial from the earliest observations, which meant that the brightness measurements were dominated by light from the dust, rather than from the nucleus directly. Estimates of the nucleus size based on simple brightness measurements would therefore be systematic overestimates, because they would attribute to the nucleus light that was actually coming from the surrounding dust cloud. The Hubble Space Telescope was used to address this problem through detailed imaging of the object at high spatial resolution. Hubble observations conducted on July 21, 2025, less than 3 weeks after the discovery, produced the first images that resolved structure within the coma and provided the basis for the first reliable estimates of the nucleus size. The Hubble image showed a teardrop-shaped cocoon of dust surrounding the central nucleus, with the coma extending substantially toward the anti-solar direction. The image allowed astronomers to estimate the contribution of the dust to the overall brightness and to extract an estimate of the nucleus brightness alone. The resulting nucleus size estimate was constrained by Hubble observations from late August 2025 to a diameter range of approximately 1,444 feet to 5.6 kilometers, or, in metric units, approximately 440 meters to 5,600 meters. The wide range of the estimate reflected the remaining uncertainty in the reflectivity assumption. If the nucleus was relatively reflective, like the cleaner surfaces of some solar system comets, then the actual size would be near the lower end of the range. If it was unusually dark, like some of the darker asteroids in our solar system, then the size could be at the upper end. The actual size was somewhere within the range, but could not be more precisely determined without additional information about the reflectivity. The range was significant because of the implications of the upper end. A 5.6 kilometer diameter would make 3I/Atlas the largest interstellar object ever detected, by a substantial margin. Oumuamua had been less than a few hundred meters in its longest dimension, with much smaller dimensions in other directions. Borisov had been approximately half a kilometer. Even the lower end of the 3I/Atlas size range, 440 meters, would make it comparable in size to Borisov and substantially larger than Oumuamua. The upper end would make it perhaps 10 times larger than Borisov in linear dimension, which corresponds to a volume more than 1,000 times larger. The statistical implications of a large size for 3I/Atlas were noted in the early scientific discussions. Larger objects should be substantially less common than smaller ones, for the simple reason that the population of small bodies in any environment tends to be heavily dominated by the smallest sizes. The number of bodies of any given size is approximately proportional to the inverse of the cube of the size, meaning that bodies 10 times smaller are typically about 1,000 times more numerous. The detection of a relatively large interstellar object as only the third interstellar visitor on record suggested either that the assumed size distribution was wrong, or that the detection process was biased in some way that made larger objects easier to detect than the simple statistical argument would suggest. The latter is probably true to some extent, because brighter objects are easier to detect, but the magnitude of the bias required to explain the observed size distribution was substantial, and itself required further investigation. The velocity of 3I/Atlas through interstellar space, before its encounter with the solar system began to affect its motion, was approximately 36 miles per second, equivalent to about 130,000 miles per hour. This is a substantial velocity by any reasonable measure, and substantially higher than the velocities of the two previous interstellar objects. Understanding what this velocity meant, how it had arisen, what it implied about the object's history, what it ruled out in terms of possible origins, became one of the early focuses of the scientific analysis of the object. The velocity of any object moving through the solar neighbourhood can be decomposed into two parts. One part is the velocity it would have if it were simply moving along with the average motion of stars in the local region, what astronomers call the local standard of rest. The other part is the deviation from that average motion, which reflects the object's individual history of gravitational interactions and perturbations. Stars and other bodies in the solar neighbourhood have a range of velocities around the local standard of rest, with most having modest deviations and a smaller number having larger deviations. The specific deviation for any particular object reflects its origin, its age, and the various perturbations it has experienced over its history. For 3I/Atlas, the calculated velocity placed it firmly in the higher velocity tail of the local interstellar population. The velocity was higher than would be expected for an object that had simply been recently ejected from a nearby planetary system, because such an object would not have had time to accumulate substantial peculiar motion through gravitational interactions with other stars. The velocity was also higher than the median for the population of stars in the local region, suggesting that 3I/Atlas had been wandering through interstellar space for a long time, long enough to have accumulated significant velocity dispersion through the cumulative effects of gravitational perturbations from many passing stars. The estimates of the age implied by the velocity, when combined with various kinematic models of how peculiar velocities accumulate over time, suggested that 3I/Atlas had been moving freely through the galaxy for billions of years. Specific estimates that emerged from detailed analyses placed the kinematic age at approximately 7 to 9 billion years, substantially older than the 4.5 billion year age of the solar system. This conclusion meant that 3I/Atlas had probably formed in some planetary system around a star that was already old by the time the Sun itself was formed, and that the original star had presumably evolved and died long before the present day. The object that astronomers were now observing was, in this sense, a fossil from a vanished planetary system, drifting through the galaxy, carrying with it whatever chemical and physical signatures had been imprinted on it during its formation in an environment that no longer exists. The high velocity also had practical implications for the observation campaign. Objects on highly hyperbolic trajectories pass through the inner solar system quickly, and the window for detailed observation is correspondingly brief. For 3I/Atlas, the period during which the object would be reasonably accessible to ground-based telescopes, bright enough, close enough, and in a favourable geometric position, was estimated at approximately 6 months, centred roughly on the perihelion passage in February 2026. Within that window, the object would be observable in various ways from various locations, but outside the window, the available observation methods would be substantially more limited. The brief window required astronomers to coordinate their observation programs carefully to maximize the scientific return from the limited time available. The trajectory direction implied by the velocity also produced interesting constraints on the object's origin. The radiant, the direction from which 3I/Atlas had been approaching before being deflected by the Sun's gravity, pointed toward the general region of the constellation Sagittarius, which is in the direction of the galactic center. This direction does not identify any specific star of origin, because the object had been perturbed by many gravitational interactions during its long journey through the galaxy, and had lost any clear memory of its original direction of motion. But the direction does provide some information about the general region of the galaxy, in which the object had spent the most recent portions of its journey, and some statistical information about the likely environment of its origin. The kinematic analysis of 3I/Atlas, taken together with the analysis of its size and orbital parameters, painted a picture of an object that was old, large, fast, and from somewhere far away. It had been drifting through the galaxy for billions of years. It had originated in a region different from the local solar neighbourhood. It had passed through countless gravitational interactions on its way to the encounter with our solar system, and it would, after that brief encounter, continue on through the V galaxy for billions more years before perhaps encountering some other star, or more likely simply continuing forever through the cold and empty spaces between them. The conclusion that 3I/Atlas is older than the solar system did not emerge from any single measurement. It emerged from the convergence of several independent lines of evidence, each of which by itself would have been suggestive but not conclusive, and which together produced a picture consistent enough that the age conclusion became, within months of the discovery, broadly accepted by the scientists working on the object. The lines of evidence came from kinematics, chemistry, and statistical comparisons to other populations of small bodies in the galaxy. None of them dated the object directly, but each constrained the age in particular ways, and the constraints converged on a value substantially greater than the age of the solar system. The kinematic evidence has already been described. The high velocity of 3I/Atlas relative to the local standard of rest, combined with models of how peculiar velocities accumulate over time through gravitational perturbations, suggested an age of at least several billion years, and probably substantially more. The kinematic age estimate is not precise. The models depend on assumptions about the local gravitational environment and the history of perturbations the object has experienced, but it consistently placed the object's age well above the age of the solar system, with central estimates in the range of 7 to 9 billion years. The chemical evidence came from spectroscopic measurements of the object's composition, particularly the measurements of certain isotope ratios. Different chemical environments in the universe produce different isotope ratios for elements like hydrogen, carbon, and oxygen. The specific ratios depend on the temperature, density, and radiation environment of the material's formation, as well as on the broader chemical evolution of the gas from which the material formed. By comparing the isotope ratios in 3I/Atlas to the ratios in solar system comets, astronomers could constrain the conditions under which 3I/Atlas had formed, and by extension, the era in the galaxy's chemical evolution when it had formed. The most striking chemical result came from measurements of the deuterium to hydrogen ratio in the water emitted by 3I/Atlas. Deuterium is a heavier isotope of hydrogen, and its abundance relative to ordinary hydrogen varies depending on the conditions of water formation. Colder environments tend to produce water with higher deuterium ratios. Measurements made using the Atacama Large Millimeter Array, published in Nature Astronomy on April 23, 2026, showed that 3I/Atlas had a deuterium to hydrogen ratio approximately 30 times higher than that found in typical solar system comets, and approximately 40 times higher than the ratio in Earth's oceans. This is an extraordinary value. It indicates that the water in 3I/Atlas formed in conditions substantially colder and possibly different in other ways from the conditions that produced water in our own solar system. The implications of the high deuterium ratio were significant. The ratio could have been produced by formation in a very cold environment, by formation in a region of low radiation, by formation in the very early universe before normal galactic chemical evolution had proceeded to the levels we observe today, or by some combination of these factors. The specific combination required to produce the observed ratio was difficult to identify uniquely, but all of the possibilities pointed toward the object being old, formed in conditions that no longer prevail in the current galaxy, in an era when the galaxy itself was younger and chemically less evolved than it is today. The statistical evidence came from comparisons of 3I/Atlas to other populations of interstellar objects. The galaxy's population of interstellar bodies includes objects of a wide range of ages, from recently ejected to extremely ancient. The properties of any specific object can be compared to the expected distribution of properties for objects of different ages, and the comparison can provide statistical constraints on the most likely age range. For 3I/Atlas, the combination of high velocity, distinctive chemistry, and large size placed it most consistently in the older portion of the expected age distribution. Younger interstellar objects would generally have lower velocities, more solar system-like chemistry, and would be drawn from a population that overlaps more closely with the population of recently formed planetary systems. 3I/Atlas did not fit that pattern. It fit better with the population of ancient objects that have been wandering through the galaxy since long before our sun was born. The convergence of these lines of evidence produced the conclusion that 3I/Atlas was, with high probability, substantially older than the solar system, probably between 7 and 9 billion years old, with substantial uncertainty in either direction. If that age is correct, then 3I/Atlas formed at approximately the same time as the oldest stars in the galaxy, in some now vanished planetary system whose central star has long since exhausted its fuel and ended its life. The object that we are observing today is a fragment of that ancient system, preserved by the cold conditions of interstellar space for the billions of years between its formation and our brief opportunity to study it. It is, in a literal sense, older than the ground beneath our feet, older than the sun in the sky, older than the framework within which all of our terrestrial life has evolved. Identifying the specific origin location of an interstellar object is, in general, impossible. The object has been drifting through the galaxy for billions of years, accumulating gravitational perturbations from countless passing stars and from the general distribution of matter in the galaxy. By the time it arrives in our solar system, its memory of its original direction of motion has been thoroughly scrambled. Even sophisticated calculations of the object's past trajectory, working backward through the gravitational potential of the galaxy, can only constrain the origin to a broad region rather than a specific point. The constraints are nevertheless interesting, because they can rule out certain types of origin while making others more probable. For 3I/Atlas, the kinematic analysis that constrained the object's age also constrained, to a limited degree, the region of the galaxy from which it had likely emerged. The high peculiar velocity of the object suggested that it had originated either in a region of the galaxy, where stars have systematically higher velocities than the local average, or that it had been perturbed onto a high-velocity trajectory by some specific gravitational interaction along its path. The first possibility implied an origin in the older stellar populations of the galaxy, the so-called thick disk and halo populations, whose members have higher random velocities and tend to be older than the stars of the thin disk in which the Sun resides. The second possibility could in principle have applied to an object of any origin, but the specific kinematic properties of 3I/Atlas were more consistent with the first explanation than with the second. The thick disk population of stars in the galaxy is older than the thin disk population. The thick disk stars formed during an earlier phase of galactic evolution, when the galaxy was undergoing more violent dynamical processes, including, possibly, the merger of the Milky Way with other smaller galaxies that contributed material to the building of the present galactic structure. The thick disk stars are systematically lower in heavy elements than the thin disk stars, reflecting the lower abundance of heavy elements in the early galaxy when these stars formed. Planetary systems formed around thick disk stars would have inherited this chemical signature, and the small bodies in those systems would carry the same chemical features. The chemical analysis of 3I/Atlas, the unusual deuterium ratio, the high CO2 content, the various other chemical peculiarities, was broadly consistent with formation in a chemically less evolved environment than that of the modern thin disk where the Sun resides. A separate strand of analysis focused on the specific trajectory direction of 3I/Atlas, and what it implied about the object's most recent perturbations. The radiant direction, as already noted, pointed toward the general region of the galactic centre. This direction does not identify a specific origin, but it does provide some information about the kinematic history of the object. Objects moving inward toward the galactic centre are, statistically, more likely to have been perturbed by the interactions with stars in the inner regions of the galaxy than by interactions with stars in the outer regions. The radiant direction was therefore broadly consistent with an origin in the older, denser inner regions of the galaxy, where the conditions for planetary system formation were different from those in the local solar neighbourhood. Specific candidate origin populations were proposed in the scientific literature. Some authors suggested that 3R/Atlas might have originated in the galactic bulge, the dense central region of the galaxy where the oldest stars in the Milky Way are concentrated. Others suggested an origin in the thick disk, perhaps in a specific stellar stream that could be identified by detailed kinematic analysis. Still others have suggested an origin in the galactic halo, the diffuse spherical population of very old stars surrounding the disk of the galaxy. Each of these possibilities was consistent with some aspects of the available evidence and inconsistent with others. None could be definitively confirmed. What was clear was that 3I/Atlas had not originated in the local solar neighbourhood. The chemical signatures were too different. The kinematic properties were too extreme. The age was too great. The object had come from somewhere far from the Sun's birthplace in some now distant part of the galaxy, around some long-dead star whose remnant, if any remained, would be unrecognizable today. The specific identification of that origin was beyond what could be determined from the available evidence, but the general nature of the origin, old, chemically distinct, kinematically extreme, was reasonably well constrained. The picture that emerged was of an object that had been part of a vanished world. Some planetary system around some ancient star had ejected the object onto an interstellar trajectory billions of years ago. The system itself had then evolved and faded. The star had run through its life cycle and ended in whatever way stars of its mass end. The object continued its journey, slowly and silently, through the cylinder spaces between the stars. After billions of years of travel, it happened to encounter the gravitational influence of a young star called the Sun. We caught a brief glimpse of it as it passed, then it continued on into the future. The chemical composition of a comet provides one of the most direct windows into the conditions under which it formed. The various ices and dust grains that compose the comet's nucleus carry the signatures of the temperature, pressure, radiation environment, and chemical evolution of the protoplanetary disk from which the comet emerged. By measuring what comes off the comet's surface as it is heated by the sun, astronomers can reconstruct, at least partially, the conditions that existed in that long-ago disk. For solar system comets, this kind of analysis has been refined over decades and provides a detailed picture of how our own planetary system formed. For interstellar comets, the same techniques can be applied, with the difference that the disk being reconstructed belonged to some other star, in some other location, at some other time. The spectroscopic observations of 3I/Atlas began within days of its discovery, using various telescopes equipped with spectrometers capable of identifying the chemical species being emitted from the comet's surface. The observations continued throughout the object's passage through the inner solar system, with each major facility contributing different pieces of the chemical picture. The James Webb Space Telescope provided infrared spectroscopy that identified specific molecular species and their abundances. The Hubble Space Telescope provided ultraviolet observations that complemented the infrared data. Ground-based telescopes provided optical spectroscopy and high spatial resolution imaging. Radio telescopes provided millimeter and sub-millimeter observations of specific molecular transitions. The combined dataset, accumulating over months of observation, produced the most detailed chemical characterization ever obtained for an interstellar object. The first chemical surprise came from the relative abundances of carbon-bearing molecules. Comets from our own solar system have characteristic ratios of carbon monoxide, carbon dioxide, and various organic molecules. The ratios vary among comets but generally fall within recognized patterns that reflect the temperature gradients in the protoplanetary disk of formation. 3I/Atlas showed ratios that fell outside these patterns. The carbon dioxide abundance was unusually high relative to water, substantially higher than the typical ratios in solar system comets. Various explanations were proposed. The object might have formed in a region of its parent protoplanetary disk, where conditions favored the preservation of CO2 ice, but not water ice. The object might have an unusual crust that prevented water sublimation while allowing CO2 to escape. The object might have been exposed to radiation conditions during its long journey that preferentially destroyed water-bearing molecules. Each explanation accounted for some aspects of the observations, but none was fully satisfactory. The second chemical surprise came from observations of water itself. The water production rate of 3I/Atlas, as measured by NASA's Swift Ultraviolet/Optical Telescope, was approximately 40 kilograms per second at the time of observation. This is a substantial water production rate, comparable to the rates produced by active comets in our own solar system. What made it surprising was the distance at which the production was occurring. At the time of the observation, 3I/Atlas was still far from the Sun, well outside the water snowline where water ice typically begins to sublimate efficiently. Yet the comet was producing water at substantial rates, indicating that something was driving water sublimation in conditions that should not normally have produced such activity. The explanation that emerged from subsequent analysis was that the activity was being driven primarily by the sublimation of carbon dioxide and other more volatile species, which entrain water molecules as they escape and produce a water signature at distances where pure water ice would not have been active. The third chemical surprise was the deuterium to hydrogen ratio in the water, already mentioned in the previous section. The value, approximately 30 times higher than typical solar system comets, was outside any range previously observed for cometary water. The measurement was made by the ALMA radio telescope array using detailed observations of specific spectral lines that distinguish water containing deuterium from ordinary water. The measurement was published in Nature Astronomy in April 2026 and represented the first deuterium ratio measurement ever made for an interstellar object. The result was conclusive evidence that 3I/Atlas had formed in conditions very different from those of the early solar system. A fourth chemical feature involved the broader pattern of molecular abundances. Various organic molecules common in solar system comets appeared to be present in 3I/Atlas at unusual ratios. The overall pattern did not match the chemical fingerprint of any known class of solar system comet, suggesting that 3I/Atlas came from a chemical environment systematically different from the one that produced our own solar system. What all of these chemical features had in common was that they pointed to a formation environment substantially colder than that of the early solar system, with lower radiation levels, and with chemical conditions that may have prevailed only in older or more distant regions of the galaxy. The chemistry was not impossible to explain through natural processes, but the specific combination of features required an unusual environment, and that environment had not previously been observed in any other known object. 3I/Atlas was, chemically, a new kind of thing. The high deuterium to hydrogen ratio in the water of 3I/Atlas deserves particular attention, because it constrains the formation environment of the object in ways that few other measurements can. The chemistry of water and its isotopes is well understood from laboratory studies and from theoretical calculations, and the conditions that produce different deuterium ratios can be specified with reasonable precision. The measurement of the ratio in 3I/Atlas therefore provides direct information about those conditions, and the inferences that can be drawn from the measurement are correspondingly firm. The deuterium to hydrogen ratio in water depends on several factors during the water's formation. The temperature of formation is the most important factor, because deuterium is preferentially incorporated into water in colder conditions. Specifically, the chemical reactions that produce water from hydrogen and oxygen atoms favour deuterium incorporation when the reactions occur at low temperatures, and disfavour deuterium incorporation at higher temperatures. The relationship between temperature and the resulting deuterium ratio is not strictly linear, but lower temperatures consistently produce water with higher deuterium content than higher temperatures. The radiation environment also matters. Water exposed to ultraviolet light or other ionizing radiation undergoes processes that can change the isotope ratio. Some processes increase the deuterium content, others decrease it. The specific effect depends on the wavelength of the radiation, the duration of exposure, and the physical state of the water. Water formed in regions of high radiation tends to have isotope ratios different from water formed in shielded regions of low radiation. The age of the formation environment matters indirectly. The galaxy has undergone chemical evolution over its history, with the abundance of heavy elements gradually increasing as successive generations of stars have produced and dispersed them. Deuterium itself is being slowly destroyed in this process, burned in the interiors of stars at temperatures too low to produce it, but high enough to destroy it. The cosmic deuterium abundance has been gradually decreasing since shortly after the Big Bang, and material formed at different epochs of cosmic history will have systematically different deuterium abundances, reflecting the universal abundance at the time of formation. Older material tends to have higher deuterium content, younger material tends to have less. For 3I/Atlas, the measured deuterium ratio of approximately 30 times the typical solar system value placed the object firmly in the high deuterium category. The simplest interpretation involved a very cold formation environment, perhaps tens of degrees above absolute zero, in regions of a protoplanetary disk far from the central star, in conditions that simply did not occur in the inner regions of the early solar system. Such conditions can exist in the outer regions of some protoplanetary disks, particularly disks around lower mass stars where the radial extent of the cold region is larger. They can also exist in dense molecular clouds, where the temperatures are uniformly low and the chemistry differs from the chemistry of a protoplanetary disk. A more elaborate interpretation involved formation in a region of low radiation in addition to low temperature. The combination would allow the high deuterium ratio to be established during formation and would prevent its subsequent modification by radiation processing during the long interstellar journey. This interpretation required the object to have formed deep within its parent protoplanetary disk, shielded from the central star's radiation, and to have remained relatively shielded during its passage through interstellar space. The specific orbital history that would produce this combination of conditions is not impossible to imagine, but does require a somewhat specific set of circumstances. An alternative interpretation involved very early formation, before the cosmic deuterium abundance had been substantially depleted by stellar processing. This interpretation required 3I/Atlas to have formed in a relatively old planetary system around a star that had itself formed in the early universe, when the deuterium fraction was higher than it is today. The interpretation was consistent with the kinematic age estimates that placed 3I/Atlas at approximately 7 to 9 billion years old. close enough to the formation of the galaxy that the cosmic deuterium abundance would have been somewhat higher than at present. The combination of an early formation epoch and a cold formation environment could account for the observed deuterium ratio without requiring either factor to be implausibly extreme. What none of these interpretations could entirely accommodate was the magnitude of the deuterium ratio. A factor of 30 is large. It places the water of 3a/Atlas at the high end of the range observed for any astrophysical environment that has been characterized in detail. Such ratios are observed in some prestellar cores, dense cold regions of molecular clouds where star formation is imminent, and in some specific protoplanetary disk environments. They are not observed in any object previously confirmed to have been delivered to a planetary system from elsewhere. 3i/Atlas therefore represents the first opportunity to directly examine the isotopic composition of water formed in a planetary system substantially different from our own. Whatever the specific formation environment that produced this water, it was not an environment that ever existed in the early solar system. The carbon dioxide content of 3i/Atlas was the second major chemical anomaly identified in the early observations, and it became in some ways even more difficult to explain than the deuterium ratio. The measurements of CO2 production were made primarily by the James Webb Space Telescope, whose infrared spectroscopy can detect the characteristic molecular signatures of CO2 even when the gas is present at relatively low concentrations. The JWST observations of 3i/Atlas, conducted in late 2025, produced detailed spectra that allowed precise measurements of the relative abundances of various molecular species in the comet's coma. The result that attracted immediate attention was the ratio of CO2 to water in the coma. In typical solar system comets, this ratio is approximately 0.1 to 0.3. That is, comets emit perhaps 10 to 30% as much CO2 as they do water. The ratio varies among comets and depends on the specific composition and the conditions under which the gas is being released, but it typically falls within this range. For 3i/Atlas, the measured ratio was approximately 1.4. This means that 3i/Atlas was emitting about 1.4 times as much CO2 as water, substantially more CO2 than water, rather than the small fraction typical of solar system comets. The implications of this ratio depended on what was actually happening at the comet's nucleus. There were two main possibilities. The first was that the nucleus contained intrinsically high amounts of CO2 ice relative to water ice, as a consequence of formation conditions that favoured CO2 condensation over water condensation. This would imply formation in a specific kind of environment where the chemistry was systematically different from the chemistry of the early solar system. The second was that the nucleus had a normal water to CO2 ratio in its bulk composition, but had some surface feature that suppressed water sublimation while allowing CO2 to escape efficiently. This would imply a particular surface structure, perhaps an insulating dust crust over a water ice-rich interior that was preventing water from being released as efficiently as CO2. A team of NASA researchers led by Martin Cordonnier explored these possibilities in detail, considering the specific physical conditions that would produce each result and the additional observations that might distinguish between them. The team's analysis suggested that the high CO2 ratio was most consistent with formation near the CO2 snowline in the parent star's protoplanetary disk, the specific distance from the central star at which CO2 ice condenses but water ice does not. Objects formed at this distance would have intrinsically CO2-rich compositions, and they would preserve those compositions throughout their long interstellar journeys. The interpretation was consistent with other features of the object's chemistry, including the high deuterium ratio, and provided a coherent picture of the formation environment that did not require any exotic processes. But the formation interpretation, while coherent, raised its own questions. The specific location of the CO2 snowline depends on the temperature structure of the protoplanetary disk, which in turn depends on the luminosity and other properties of the central star. For typical Sun-like stars, the CO2 snowline is at distances of perhaps 10 to 30 astronomical units, far from the inner regions where Earth-like planets form, but well within the typical extent of a protoplanetary disk. Objects formed at the CO2 snowline could be ejected from the parent system through the same kinds of gravitational interactions that produce other interstellar objects, and they would carry their CO2-rich composition with them into interstellar space. What was unusual was that the resulting population of CO2-rich interstellar objects had not previously been identified. 2i/Borisov, the only previous interstellar comet with detailed chemical characterization, had a relatively normal water to CO2 ratio more consistent with formation in less extreme conditions. The discovery that Threa/Atlas was so different from Borisov in this respect suggested that the population of interstellar objects might be substantially more diverse than the two-object sample had previously implied. There might be objects with all kinds of compositions, from water-rich to CO2-rich to other compositions yet unobserved. Each interstellar object would carry the signature of its specific formation environment, and the population as a whole would represent the diversity of planetary system environments throughout the galaxy. The CO2 anomaly was therefore both a specific puzzle about 3I/Atlas and a window into a broader picture of galactic chemistry. The high CO2 content of the object was unusual, but the existence of such an unusual object suggested that the galactic population of interstellar objects might include a wide range of compositions reflecting a wide range of formation environments. Future observations of additional interstellar objects, as they are discovered, would either confirm this expectation by revealing additional chemical diversity, or would surprise astronomers by showing that 3I/Atlas is a unique outlier rather than a representative of a broader population. Either result would teach us something significant about the chemistry of the galaxy and about the diversity of conditions under which planetary systems form. The CO2 anomaly was, in this sense, not just a feature of one object, but the first hint of a much larger story about how the galaxy is chemically structured. When comets approach the Sun, they undergo a characteristic transformation. As they move from the cold outer regions of the solar system into the warmer inner regions, the ices on their surfaces begin to sublimate, to convert directly from solid to gas without passing through a liquid phase. The sublimating gases carry dust grains with them as they escape from the comet's surface, and this combination of gas and dust forms the characteristic features of an active comet, the diffuse glowing cloud called the coma that surrounds the nucleus, and this long streaming tail that extends away from the Sun. The transformation from a quiet frozen body to an active comet is one of the most visually striking phenomena in the solar system, and it has been observed and studied for centuries. The specific distance at which a comet becomes active depends on what kinds of ices are present on its surface. Water ice, the most common cometary ice in our solar system, sublimates efficiently when comets are within approximately 3 astronomical units of the Sun, 3 times the distance from the Earth to the Sun. This distance is sometimes called the water snow line, though the term is also used in slightly different senses in other contexts. Inside the water snow line, water ice sublimates rapidly enough to produce visible cometary activity. Outside it, water ice remains essentially inert. Comets approaching the Sun from the outer solar system typically remain quiet until they cross the water snow line, at which point they begin to develop comas and tails that grow in intensity as they get closer to the Sun. More volatile ices, such as carbon dioxide and carbon monoxide, sublimate at greater distances. CO2 ice can sublimate at distances of perhaps 10 astronomical units from the Sun, far outside the water snow line. CO ice can sublimate even farther out, at distances of 30 astronomical units or more. Comets that contain significant amounts of these more volatile ices can therefore begin to show activity well before they cross the water snow line, with the early activity being driven by the volatile ice sublimation rather than by water. Threa/Atlas was first observed showing significant cometary activity at distances well outside the water snow line. The Hubble Space Telescope image from July 21, 2025, showed a clear coma surrounding the nucleus, with a teardrop-shaped extension toward the antisolar direction. At the time of this observation, the comet was approximately 277 million miles from Earth, a distance corresponding to about 3 astronomical units, which is approximately at the water snow line. But subsequent observations from various telescopes revealed that the activity had been present at even greater distances, with brightness measurements suggesting that the comet had been active since substantially before its discovery. The activity at large heliocentric distances was consistent with the chemical analysis suggesting that 3A/Atlas contained substantial amounts of CO2 and other volatile ices. The CO2 sublimation could drive activity at distances where water alone would not have produced visible signs of life. The water that was being released, as measured by NASA's Swift Ultraviolet/Optical Telescope, was being entrained by the more volatile gases as they escaped from the nucleus surface, producing a water signature even though pure water ice sublimation would have been minimal at those distances. The implications of the distant activity were significant for several reasons. First, it confirmed the chemical interpretation that 3I/Atlas was a volatile rich object. Second, it meant that the object was observable for a longer period than would have been possible for a less active comet at similar distances. Comets that develop activity only after crossing the water snowline have relatively short observation windows, because they are inactive and faint before reaching the snowline. 3I/Atlas, with its early activity, was observable in detail for the entire period from its discovery through its perihelion passage, providing a much longer baseline of observations than would otherwise have been available. Third, the early activity provided opportunities for specific kinds of measurements, particularly the chemical characterization of the gases being released that required active sublimation to produce detectable signals. The pattern of activity also evolved in interesting ways as 3I/Atlas approached the Sun. The initial activity was relatively modest, dominated by CO2 sublimation. As the comet moved closer to the Sun and the surface temperature increased, water sublimation became more significant, and the relative abundances of different gases in the coma shifted accordingly. The observations during this transition period provided detailed information about the thermal evolutions of the comet's surface and about how the various ices were distributed within the nucleus. The picture that emerged was of a complex layered object whose response to solar heating evolved in ways that reflected both the bulk composition and the surface structure. The distant activity was, in itself, not anomalous in the strict sense. It was consistent with standard cometary physics. But it was unusual in degree, more extensive than would have been expected for a typical comet, and it contributed to the picture of 3I/Atlas as an object that differed in important ways from the comets of our own solar system. The orientation of a comet's tail is determined by physics that has been understood for centuries. The tail consists of gas and dust that have been released from the comet's nucleus, and are then pushed away from the Sun by the combined effects of solar radiation pressure and the solar wind. The direction of the push depends on the direction from which the sunlight is coming, which means the tail always extends in the anti-solar direction, pointing away from the Sun, regardless of the direction the comet itself is moving. Comets that are moving outward from the Sun have tails behind them. Comets that are moving inward toward the Sun have tails ahead of them. The tail is, in this sense, a direct visualization of the radial direction from the Sun, rather than a feature of the comet's own motion. In actual observation, comet tails often appear to point in directions slightly different from the strictly anti-solar direction. The deviations result from various effects. Dust grains having mass are pushed less efficiently by radiation pressure than gas molecules are, and they retain some of the comet's own motion as they are released. The result is that the dust tail typically curves slightly behind the comet's path, while the gas tail points more directly in the anti-solar direction. The two tails may therefore appear at slightly different angles, and the overall tail structure can be complex, but the general principle holds. Tails point away from the Sun, with modest deviations that can be calculated from the physics of the various forces acting on the tail material. When the first detailed images of 3I/Atlas became available, the Hubble image of July 21, 2025, and subsequent images from various telescopes, the tail structure visible in the images appeared to be more complex than would have been expected from a typical comet. The teardrop-shaped cocoon of dust extended toward the anti-solar direction in the expected sense, but the overall structure included features that did not fit the standard tail geometry. Specific elongations and asymmetries were noted by analysts examining the images. The patterns were not so dramatic as to be obviously inexplicable by standard physics, but they were noticeably different from the cleaner tail structures typically seen in solar system comets. The detailed analysis of the tail geometry was conducted by several research teams using the various images that became available during the comet's transit. The analyses considered the various physical effects that could produce the observed structures, including the specific size distribution of dust grains being released from the nucleus, the rotation of the nucleus, the temporal evolution of the activity, and various other factors. The conclusions varied somewhat among different analyses, but the general picture that emerged was of a tail structure that could be explained by standard cometary physics if certain assumptions were made about the activity pattern of the nucleus. One specific feature attracted particular attention. Some of the images appeared to show a slight forward component to the tail, a small but detectable extension of dust in the direction of the comet's motion, rather than purely in the anti-solar direction. This is sometimes called an anti-tail in the literature, and it can occur in solar system comets under specific geometric conditions. The conditions involve a comet whose nucleus has been releasing dust that has accumulated over time in the orbital plane of the comet, and which is being seen from Earth at a particular geometric configuration that makes the accumulated dust appear in the forward direction. Anti-tails in solar system comets are well understood phenomena, and their occurrence does not require any unusual physics. For 3I/Atlas, the apparent anti-tail feature was attributed to the standard mechanism by most analysts. The specific geometric configuration of the comet's orbit relative to Earth's line of sight, combined with the dust distribution that would have accumulated during the comet's approach to the Sun, was consistent with the appearance of a forward dust extension under conditions like those that produce anti-tails in solar system comets. The interpretation was not entirely uncontested. Some researchers suggested that the specific characteristics of the feature were difficult to fully account for through the standard mechanism, but the mainstream view was that the feature was a normal cometary phenomenon rather than evidence of any unusual physics. The tail structure of 3I/Atlas thus represented, in the mainstream interpretation, a more complex but still natural example of cometary tail formation. The standard physics could account for the observations if appropriate assumptions were made about the dust distribution and the geometry of observation. The alternative interpretation, that some unusual non-gravitational force was producing tail features that could not be explained by standard mechanisms, was considered by some researchers but was not widely adopted in the scientific community. Like many features of 3A/Atlas, the tail geometry was unusual enough to require careful analysis, but not so unusual as to definitively require any new physics. The pattern, by this point in the discussion, was becoming familiar. The object was strange in many ways, but always within the boundaries of what standard physics could potentially explain, even if the specific explanations required somewhat unusual assumptions in each case. The James Webb Space Telescope had been operating in space for approximately 3.5 years when 3I/Atlas was discovered. The telescope, launched in December 2021 and operational since mid-2022, is the most powerful space telescope ever built, with capabilities optimized for infrared observation that complement the visible light capabilities of the older Hubble Space Telescope. JWST has been used to study a wide range of astrophysical objects, from the most distant galaxies in the early universe to specific features in our own solar system. The discovery of an interstellar comet within the telescope's observable range was an opportunity that the JWST team recognized immediately, and a coordinated program of observations was developed to use the telescope's unique capabilities for the study of 3I/Atlas. The specific instruments on JWST that were used for the observations included the near-infrared spectrograph, abbreviated NIR-SPEC, and the mid-infrared instrument MIRI. NIR-SPEC provides spectroscopy at wavelengths from approximately 0.6 to 5 micrometers, allowing the identification of various molecular species through their characteristic absorption and emission features in this wavelength range. MIRI extends the spectroscopy to longer wavelengths, from approximately 5 to 28 micrometers, where additional molecular features can be detected and where thermal emission from the comet's nucleus and surrounding dust can be measured. The combination of these instruments provides comprehensive infrared coverage of the comet's emission, allowing detailed chemical analysis that complements the optical and ultraviolet observations from other facilities. The first JWST observations of 3I/Atlas were conducted in August 2025, approximately 1 month after the discovery. The observations produced spectra that immediately revealed several of the chemical features that would become central to the scientific characterization of the object. The carbon dioxide signature was particularly strong, with the CO2 molecular emission appearing as a clear feature in the mid-infrared spectrum. Water emission features were also detected, allowing the relative abundance of water to be measured against the CO2. Various other molecular species were identified, including carbon monoxide, methanol, and several other organic compounds. The relative abundances measured by JWST became the basis for the chemical characterization of the comet. The high CO2 to water ratio was first quantified from these observations, with the resulting value of approximately 1.4 being substantially different from the typical solar system comet values. The high deuterium ratio was inferred from the JWST data, though the more precise measurement that was eventually published came from ALMA observations using a different technique. the general picture of an unusual chemical composition emerged from the JWST observations more clearly than from any other single source. Beyond the chemical analysis, the JWST observations also provided information about the physical properties of the comet's coma and tail. The thermal emission measured at longer wavelengths revealed the temperature distribution within the coma, with the inner regions being hotter than the outer regions in a pattern consistent with the standard physics of cometary comas. The spatial structure of the emission, resolved by the JWST's high spatial resolution, provided information about the size distribution of dust grains and the dynamics of the gas-dust mixture being released from the nucleus. The detailed spatial analysis was published in several scientific papers in the months following the observations, contributing to the comprehensive picture of the object that gradually emerged. The JWST observations had specific advantages over ground-based observations in several respects. The infrared spectroscopy was conducted without atmospheric absorption, which severely limits ground-based infrared observation. The spatial resolution was higher than what could be achieved from the ground, allowing fine details of the coma structure to be resolved. The sensitivity was greater than ground-based observations, allowing detection of faint emission features that would have been below the detection threshold of ground-based instruments. The combination of these advantages made JWST one of the most valuable facilities for the study of 3I/Atlas, and the data it collected formed a major portion of the scientific basis for the eventual analyses. The observations also had some limitations. JWST observation time is a scarce resource, and the time allocated to 3I/Atlas observations was necessarily limited compared to the time that would have been allocated to a major project like the study of an exoplanet atmosphere or a distant galaxy. The observations were therefore relatively brief, focused on specific high-priority measurements rather than on a comprehensive characterization. Additional observations would have provided more detailed information, but the trade-off with other scientific priorities meant that the JWST contribution to the 3I/Atlas characterization was substantial but not exhaustive. What the JWST observations established, when combined with data from other facilities, was that 3I/Atlas was chemically distinct from any previously characterized comet. The combination of high CO2, high deuterium, and various other features placed the object in a category by itself. JWST had been built to study the most distant and ancient objects in the universe. The opportunity to use it to study an ancient object passing through the solar system at exactly the right time was a fortunate coincidence, and the resulting data have provided some of the most detailed information ever obtained about a planetary system other than our own. The Hubble Space Telescope has been in orbit for more than 3 decades, and it remains one of the most productive astronomical facilities in operation, despite the existence of newer and more powerful telescopes. Hubble's combination of high spatial resolution in visible light, broad wavelength coverage from ultraviolet through near-infrared, and remarkable long-term stability makes it irreplaceable for many kinds of observations. For 3I/Atlas, Hubble was used to obtain high-resolution images that allowed detailed analysis of the comet's structure, particularly the relationship between the central nucleus and the surrounding dust coma. The first Hubble image of 3I/Atlas was obtained on July 21, 2025, 3 weeks after the initial discovery. The image was taken with the Wide Field Camera 3, Hubble's primary imaging instrument, using filters that maximize the contrast of the comet against the background stars. At the time of the observation, the comet was approximately 277 million miles from Earth, close enough for Hubble's high spatial resolution to resolve fine structure in the coma, but far enough that the comet itself appeared as a small compact object with surrounding diffuse emission. The image, when published shortly after the observation, became one of the most widely circulated astronomical images of 2025. It showed the comet as a small bright point at the center of an obvious teardrop-shaped cocoon of dust and gas. The teardrop shape extended toward the anti-solar direction, consistent with the standard pattern of cometary coma development. The compact central feature was identified as the nucleus and the surrounding dust, with the more diffuse extension being the developing tail. The background stars in the image appeared as short streaks rather than points, reflecting the fact that Hubble had been tracking the comet's motion during the exposure, with the result that the stationary stars in the background were trailed by the relative motion. The Hubble observations were used to make the first reliable estimates of the nucleus size. By carefully separating the contribution of the nucleus from the surrounding dust contribution, the Hubble team estimated the upper limit on the nucleus diameter to be 3.5 miles, or approximately 5.6 kilometers, with the lower limit being approximately 440 meters. The wide range reflected the uncertainty in the reflectivity assumption needed to convert brightness to size, but the upper limit was reliable in the sense that the nucleus could not be larger than approximately 5.6 kilometers given the observed brightness. The image also revealed structural details that contributed to the scientific characterization of the object. The shape of the coma, the relative brightness of different regions, the apparent extent of the activity. All of these features were analyzed in detail using the high-resolution Hubble image as the primary data source. The image was followed by additional Hubble observations over the subsequent months, each providing additional information about how the comet's appearance evolved as it approached the Sun and as the activity increased. The image also became the focal point of public discussion about 3I/Atlas. The teardrop shape, with its compact bright center and surrounding diffuse cloud, was visually striking and was widely reproduced in news coverage, scientific presentations, and social media discussions of the object. For many people who became aware of 3I/Atlas during this period, the Hubble image was the first concrete visual representation of the object they encountered, and it shaped their initial impressions of what they were seeing. The image was also the basis for some of the early speculation about the nature of the object. Various commentators noted that the structure visible in the image could be interpreted in different ways. The standard cometary interpretation, that the bright central feature was a nucleus surrounded by a dust coma, was the mainstream view and was supported by the developing chemical evidence. But alternative interpretations were proposed by some commentators, particularly Avi Loeb and others associated with the proposal that 3/Atlas might be artificial. Loeb argued that certain features of the image, the specific brightness profile, the apparent geometry of the structure, the absence of certain expected cometary features, could be interpreted as more consistent with an artificial object surrounded by a deliberately produced cloud of debris than with a natural comet. The argument was controversial. Most astronomers rejected the alternative interpretation, but the discussion continued in various venues and contributed to the broader public interest in the object. What the Hubble image demonstrated, regardless of the specific interpretations applied to it, was that 3I/Atlas was a substantial, well-developed object showing clear signs of activity, even at the substantial distances at which it was being observed. The image provided concrete visual evidence of the existence of the object and its general structure, anchoring the various spectroscopic and other measurements that were being made in parallel. The image would be reproduced and analyzed countless times in the months that followed, and it would remain one of the iconic images associated with 3I/Atlas for as long as the object continued to be discussed. It was the picture that made the discovery real for many observers, the first clear visual confirmation that something was indeed passing through the solar system, regardless of what it actually was. On July 16, 2025, approximately 2 weeks after the discovery of 3I/Atlas, a paper was posted to the ARXUAE preprint server by Avi Loeb of Harvard University and several collaborators from the Initiative for Interstellar Studies. The paper argued that certain features of 3I/Atlas were difficult to explain through standard cometary physics, and that the most economical interpretation of these features was that the object might be an extraterrestrial spacecraft. The paper was, by the standards of mainstream astronomy, an extraordinary claim. It generated immediate and substantial response in the astronomical community, the popular press, and the broader public discussion of the object. The paper would shape the discussion of 3I/Atlas for the remainder of its passage through the solar system, regardless of whether its specific arguments were ultimately accepted. Avi Loeb is a prominent figure in modern astronomy. He has held senior positions at Harvard for decades, has published hundreds of scientific papers across a wide range of topics, and has produced major contributions to the understanding of the early universe, black holes, and various other subjects. He has also become, in recent years, the most prominent advocate within the professional astronomical community for serious consideration of the possibility that some observed astronomical phenomena might be of artificial origin. His previous arguments about Oumuamua had been widely discussed and largely rejected by the mainstream astronomical community. His arguments about 3/Atlas were a continuation of the same general line of inquiry applied to the new object. The specific arguments in the Loeb paper involved several features of 3I/Atlas. The first was the trajectory of the object, which Loeb and his colleagues argued had certain features that would be statistically improbable for a randomly drawn interstellar object. The trajectory brought 3I/Atlas into relatively close proximity with several planets, Mars, Earth, Jupiter, at intervals that the author suggested were unusual for a random encounter. The probability of any specific trajectory bringing an object close to multiple planets is, in principle, calculable, and the authors argued that the calculated probability for the actual trajectory was low enough to warrant consideration of non-random explanations. The second argument involved the chemical and physical properties of the object. The unusual CO2 ratio, the high deuterium content, the early activity at large heliocentric distances, the various other anomalies. Loeb argued that the combination of these features was statistically improbable for a natural object drawn from any plausible population of interstellar comets. The argument was not that any single feature was impossible to explain through natural processes, but that the specific combination of features made the natural origin interpretation less probable than the alternative of artificial origin. The third argument involved the size of the object. If the nucleus diameter was near the upper end of the Hubble-derived range, approximately 5.6 kilometers, then 3I/Atlas would be substantially larger than would be expected for a random interstellar object detected this early in the era of systematic interstellar object surveys. The expected size distribution for interstellar objects is heavily weighted towards smaller sizes, and the detection of a large object as only the third confirmed interstellar visitor was statistically improbable under the assumption of a natural population. Loeb argued that the size, combined with the other features, was more consistent with an object that had been selected or constructed for specific purposes than with a random sample of the natural population. The Loeb paper acknowledged that the artificial origin interpretation was speculative and that the natural origin interpretation was more likely on the basis of prior expectations. But the paper argued that the artificial origin interpretation was worth considering as a serious hypothesis, that specific tests could be designed to distinguish between the two interpretations, and that the scientific value of taking the hypothesis seriously justified the effort required to investigate it. The response to the paper was immediate and substantial. Many astronomers criticized the specific statistical arguments, pointing out that the probability calculations involved various assumptions that could be reasonably questioned. Some critics argued that the selection effects involved in detecting interstellar objects systematically favored the detection of objects with certain features, large size, high activity, favorable trajectory, and that the apparent improbability of these features in 3I/Atlas reflected the bias of the detection process rather than any inherent improbability of the object itself. Others argued that the artificial origin hypothesis was so unprecedented that the standards of evidence required to accept it should be correspondingly high, and that the evidence presented in the paper, while suggestive, fell far short of those standards. Loeb himself, in subsequent statements, was careful to note that even he considered the natural origin interpretation more likely than the artificial origin interpretation. He described the analysis as an exercise in considering an unusual hypothesis seriously, rather than as a definitive argument that 3I/Atlas must be artificial. The distinction was sometimes lost in the popular discussion, where the paper was often characterized as Loeb claiming that 3I/Atlas was extraterrestrial technology. The actual content was more nuanced, but the nuance was difficult to maintain in the broader public discussion that followed. The trajectory argument in the Loeb paper deserves more detailed examination because it became one of the most discussed and most contested elements of the broader case for considering an artificial origin for 3I/Atlas. The argument centered on a specific feature of the trajectory, the relatively close approaches that 3I/Atlas would make to several of the planets during its transit through the inner solar system. The argument was that these close approaches were statistically improbable for a randomly oriented interstellar trajectory, and that the improbability constituted evidence in favor of some non-random origin. The specific close approaches in question were to Mars, Earth, and Jupiter. 3I/Atlas would pass within approximately 18 million miles of Mars in October 2025, close enough to allow observations from Mars orbiters but far enough that no direct interaction with the planet would occur. It would pass within approximately 170 million miles of Earth in December 2025, which is close by interstellar standards but distant by the standards of solar system encounters. It would pass within approximately 32 million miles of Jupiter in March 2026, again close enough for spacecraft observations but well outside the range of any direct interaction. The probability calculation in the Loeb paper estimated the likelihood that a random trajectory through the inner solar system would happen to bring the object within the specified distances of these 3 planets. The calculation involved various assumptions about the distribution of possible trajectories and the relevant distance thresholds. The result, as presented in the paper, suggested that the probability was small, or perhaps a few percent or less, depending on the specific assumptions used. The authors argued that this small probability made the actual trajectory unusual enough to warrant consideration of non-random explanations. The criticisms of this argument focused on several aspects. The most fundamental criticism was that the probability calculation depended on the specific thresholds chosen for what counts as a close approach. By choosing different thresholds, the calculated probability could be made larger or smaller. The argument that the calculated probability was suspiciously small therefore depended on the specific thresholds being treated as natural rather than as parameters chosen to produce the desired result. Critics argued that the trajectory was not actually as unusual as the calculation suggested, and that with different thresholds the trajectory would appear unremarkable. A second criticism involved the selection effects in the discovery of interstellar objects. The ATLAS survey that discovered 3I/Atlas was specifically optimized to detect objects that might pose impact hazards to Earth. The survey's design therefore biased it toward the detection of objects on trajectories that brought them relatively close to Earth, because such trajectories were the ones the survey was designed to find. Objects on trajectories that did not bring them close to Earth would be less likely to be detected by the survey, even if they had similar properties otherwise. The discovery of an interstellar object on a trajectory that included a close Earth approach was therefore not particularly surprising given the survey's design, and the trajectory could not be used to argue for non-random origin without accounting for the selection effect. A third criticism involved the broader population of solar system encounters. The orbits of the planets are not randomly distributed in space. They all lie approximately in a single plane called the ecliptic, with relatively small inclinations from one another. An object passing through this plane has a higher probability of close encounters with planets than would be the case if the planetary orbits were randomly oriented. The trajectory of 3I/Atlas happened to lie relatively close to the ecliptic plane, which increased the probability of multiple planetary encounters. The argument that the trajectory was improbably aligned with multiple planets was therefore weaker, once the geometry of the solar system itself was taken into account. A fourth criticism, more subtle, but perhaps most fundamental, involved the question of which specific trajectory features should be considered as evidence. Any specific trajectory is, in some sense, improbable when described in sufficient detail. The exact path through space, the exact timing of various events, the exact geometric relationships with various other objects. The question of which features are significant and which are coincidental is a judgment call that depends on the prior assumptions of the analyst. Critics argued that the features highlighted in the Loeb paper were chosen specifically because they were unusual, and that other features of the trajectory that were perfectly ordinary were ignored. By cherry-picking the unusual features and ignoring the ordinary ones, the calculation could be made to appear more impressive than it actually was. The overall assessment by the mainstream astronomical community was that the trajectory argument was suggestive but not compelling. The trajectory was indeed unusual in certain specific respects, but the various selection effects and methodological issues meant that the apparent unusualness could not be taken as strong evidence for non-random origin. The argument continued to be discussed in various venues, but it did not produce a substantial shift in the mainstream view that 3I/Atlas was most likely a natural object. In the autumn of 2025, 3I/Atlas moved into a region of the sky where it could not be observed from Earth-based telescopes. The geometry was simple. The Earth orbits the Sun once per year, and during the course of that orbit, different regions of the sky are visible at different times. Objects whose positions are close to the direction of the Sun, as seen from Earth, cannot be observed because the bright sunlight overwhelms the much fainter light from the object itself. The Sun must be at least some minimum angular distance away from an object before that object can be observed against the dark background scheme. The specific minimum angle depends on the brightness of the object. Bright objects can be observed closer to the Sun than faint ones, but for typical telescopic observations, the minimum angle is approximately 15 to 20 degrees. For 3I/Atlas, the geometry of the trajectory and the Earth's orbital motion combined to produce a period during which the object would be too close to the Sun as seen from Earth to be observed. This period, called the solar conjunction, was predicted to begin in approximately mid-October 2025 and to continue for several weeks, ending in early December 2025. During this period, ground-based telescopes would not be able to observe 3i/Atlas, and many space-based telescopes, including Hubble, would also be limited or unable to observe due to similar geometric constraints. The implications of the solar conjunction were significant. The period of conjunction included the time when 3i/Atlas would be at its closest to the Sun, the perihelion passage, originally predicted for February 2026, but with the actual closest approach occurring during the conjunction period. The most intense solar heating, and therefore the most active cometary behaviour, would occur during this period. The most chemically interesting observations would have been those made at the time of maximum activity, when the various ices on the comet's surface were sublimating most rapidly and producing the strongest spectroscopic signals. But the perihelion would occur when Earth-based and most Earth-orbiting observers could not see the object, and the most active period of the comet's transit would be entirely outside the standard observation window. The astronomical community responded to this constraint by mobilizing the various spacecraft that were positioned in ways that allowed them to observe 3i/Atlas during the solar conjunction. Mars orbiters, which are located near Mars rather than near Earth, had a different geometric relationship with 3i/Atlas and could observe the object during periods when Earth-based observers could not. The Europa the Clipper spacecraft, which had been launched in October 2024 and was travelling toward the Jovian system, was positioned to potentially intercept the ion tail of 3i/Atlas during a specific period in late October and early November 2025. Various other spacecraft, Lucy, Psyche, Parker, Solar Probe and others, were also positioned to provide observations during the conjunction period. The Europa Clipper observations were particularly interesting because they represented an unprecedented opportunity to directly sample the material in an interstellar comet's tail. The spacecraft would not encounter the comet itself, which was hundreds of millions of miles away, but it would pass through the diffuse ion tail extending outward from the comet. The ions in the tail had been emitted from the comet's nucleus, accelerated outward by the solar wind, and were drifting through space along the magnetic field lines of the interplanetary medium. By measuring the ions and the associated magnetic field disturbances as the spacecraft passed through the tail, the Europa Clipper team could obtain direct compositional information that complemented the remote spectroscopic observations from telescopes. The conjunction period therefore represented both a constraint and an opportunity. The constraint was that traditional Earth-based observation had to pause for several weeks during the most scientifically interesting portion of the comet's transit. The opportunity was that less traditional observation methods, spacecraft instruments, in situ measurements, observations from non-Earth perspectives, could fill in the gap and could in some cases provide information that Earth-based observation would never have been able to obtain. The combination of constraint and opportunity shaped the observation campaign in important ways, distributing the scientific effort across multiple facilities and producing a more diverse dataset than would have resulted from a campaign focused primarily on Earth-based observation. The conjunction also had a more subtle effect on the public discussion of the object. During the weeks when 3i/Atlas could not be observed from Earth, the flow of new information about the object slowed substantially. The press coverage diminished. The social media discussion shifted to other topics. The intense public interest that had accompanied the early observations gradually faded, as it always does when news flows are interrupted for extended periods. By the time the conjunction ended and Earth-based observation resumed, the object had become less of a public phenomenon and more of a specialist scientific subject. The intense initial response had passed, and the more sustained scientific study could proceed without the constant accompaniment of public speculation that had characterized the first few months after the discovery. The period of solar conjunction, during which 3i/Atlas was not directly observable from Earth, was not actually a period of zero observation. Various spacecraft and specialized facilities continued to monitor the object throughout the conjunction, producing data that filled in much of the gap that Earth-based observation could not cover. The observations during this period were technically more difficult to obtain and produced data of generally lower spatial and spectral resolution than what could be obtained when Earth-based observation resumed. But they were valuable for the simple reason that they covered the most active phase of the comet's transit through the inner solar system, when the most rapid changes in the object's behavior were occurring. The first category of observation came from spacecraft in orbit around Mars. The Mars Reconnaissance Orbiter, MAVEN, and the Perseverance rover all conducted observations of 3I/Atlas during its closest approach to Mars in October 2025. The closest approach distance, approximately 18 million miles, was close enough that Mars-based observations had geometric advantages over Earth-based observations during the same period. The Mars orbiters were on the opposite side of the Sun from Earth during portions of the relevant period, which meant they could observe 3I/Atlas in directions that were inaccessible from Earth. The resulting data included imagery from the orbiter's cameras and spectroscopy from the various instruments designed primarily for Mars science, but adaptable to other targets. The European Space Agency's Mars Express orbiter also conducted observations of 3I/Atlas during this period, and the ESA's Trace Gas Orbiter contributed its own observations using the higher resolution imaging capabilities developed for Mars studies. The combined Mars-based observations produced detailed information about the comet during a phase of its transit when Earth-based observation was not possible, including measurements of the activity level, the spectral characteristics of the emission, and the structural development of the coma and tail. The second category of observation came from spacecraft positioned at various locations elsewhere in the solar system. The Europa Clipper observations mentioned in the previous section were among the most scientifically significant. The spacecraft was traveling toward the Jupiter system and happened to be positioned along a path that would pass through the ion tail of 3I/Atlas in late October and early November 2025. The trajectory had not been designed to intersect the ion tail. The encounter was an accident of the spacecraft's mission timing and the comet's trajectory, but once the alignment was recognized, the Europa Clipper team modified the planned instrument operations to maximize the scientific return from the encounter. The spacecraft's various instruments measured the ion environment, the magnetic field, and the energetic particle population during the period when it was inside the ion tail, producing the first direct in situ measurements of material from an interstellar object. The ESA Hera spacecraft, traveling on its own mission toward the binary asteroid system Didymos, was similarly positioned for a tail crossing in late October and early November 2025. The Hera observations complemented those from Europa Clipper, providing measurements from a different location and with different instruments. The Lucy and Psyche spacecraft, both NASA missions to study small bodies elsewhere in the solar system, also contributed observations from their respective trajectory positions. Each of these spacecraft provided a different viewpoint and a different combination of instrument capabilities, and the aggregate result was a multi-perspective dataset that was richer in some respects than what could have been obtained from any single observation platform. The third category of observation came from specialized facilities that could observe close to the Sun direction. The Solar and Heliospheric Observatory, or SOHO, has been operating since 1995 and is specifically designed to observe the Sun and its immediate environment. Comets sometimes pass close enough to the Sun to be visible in SOHO's coronagraphs, which are instruments that block out the bright solar disk to allow observation of the much fainter solar corona and nearby objects. During the conjunction period, 3I/Atlas came within the field of view of SOHO's coronagraphs, allowing the comet to be observed even when it was very close to the Sun. The observations were of modest spatial resolution and provided information about the overall brightness and apparent structure of the comet during the brightest portion of its passage near the Sun. The Parker Solar Probe, NASA's mission to study the Sun at close range, was also positioned in ways that allowed certain observations of 3I/Atlas during portions of the conjunction period. Parker's instruments are designed primarily for solar measurements, but can be used in various ways to observe other phenomena in the inner heliosphere. The contributions from Parker were less extensive than those from some other spacecraft, but added to the overall observational coverage during the period. The combined dataset from the various spacecraft and specialized facilities produced a substantially complete record of 3I/Atlas's behavior during the conjunction period. When Earth-based observation resumed in December 2025, the resulting picture of the comet's transit was nearly continuous from discovery through perihelion and beyond, with only modest gaps in coverage. The various data sources were combined in subsequent analyses to produce the comprehensive picture of the object's behavior that has formed the basis for the scientific characterization. On March 16, 2026, approximately 1 month after the perihelion passage near the Sun, 3I/Atlas passed relatively close to the planet Jupiter. The closest approach distance was approximately 32 million miles, close enough for various observation campaigns to take advantage of the geometry, but far enough that no direct gravitational interaction with Jupiter would significantly alter the comet's trajectory. The Jupiter flyby was, in many respects, the second major observational event of the comet's transit through the solar system, comparable in scientific importance to the original discovery and the perihelion passage. The geometry of the Jupiter flyby had several advantages for observation. Jupiter is the largest planet in the solar system, and it is closer to the inner solar system than the outer regions where the comet would soon be heading. Jupiter is also home to several spacecraft that were positioned to observe 3DO or I/Atlas during the flyby. The Juno spacecraft, which had been studying Jupiter since 2016, was still operating in Jovian orbit and could conduct observations of the comet during the flyby. The Europa Clipper spacecraft, which had encountered the comet's ion tail in late 2025, was approaching Jupiter and could potentially be repositioned to observe the comet from closer range. The European Space Agency's JUICE spacecraft, the Jupiter Icy Moons Explorer launched in 2023, was also in transit toward Jupiter and was in a position to observe 3I/Atlas during the flyby. The JUICE observations turned out to be particularly significant. The spacecraft's Janus camera, designed for imaging the icy moons of Jupiter, was used to obtain detailed images of 3I/Atlas during the flyby period. The images, released by ESA in early April 2026, showed the comet at a level of detail that exceeded what had been possible from Earth-based observation during the comet's earlier transit. The Janus images revealed the structure of the coma and tail at high spatial resolution, the temporal evolution of the comet's brightness during the encounter period, and various other details that contributed to the scientific characterization. The ESA's release of the Janus images in April 2026 became something of a media event. The images were widely circulated and discussed in popular media, and they provided new visual material for the public discussion of 3I/Atlas, at a time when public interest in the object had begun to fade after the discovery. The release coincided with the publication of the major chemical analysis papers, including the deuterium ratio measurement published in Nature Astronomy on April 23, 2026, and the combination of new imagery and new chemical results produced a renewed wave of public attention to the object. The last month of unusual activity referenced in many discussions during this period was substantially the activity associated with the Jupiter flyby and the publications that followed. The Jupiter flyby also provided an opportunity for direct gravitational analysis. While the encounter was too distant to significantly alter the comet's trajectory, it was close enough that small gravitational effects could be measured. These measurements provided independent confirmation of the comet's mass and orbital parameters, complementing the measurements made through other means. The mass measurements were significant because mass is one of the few fundamental properties of a comet that cannot be directly measured through standard remote observation techniques. It must be inferred from gravitational effects or from indirect arguments based on size and density. The Jupiter flyby provided one of the few opportunities for direct mass-related measurements. The resulting constraints were valuable for the overall characterization of the object. The scientific products of the Jupiter flyby were published in a series of papers in the months that followed. The papers covered various aspects of the encounter, from the Janus imaging to the in situ measurements by spacecraft that had been close enough to make detailed observations. The aggregate scientific output from the flyby was substantial, comparable to the output from the original discovery period and from the perihelion passage. The flyby thus became one of the major scientific milestones in the study of 3I/Atlas, contributing substantially to the developing picture of the object's properties and history. For the public, the Jupiter flyby served as a kind of farewell event. After the flyby, 3I/Atlas would be moving outward from the inner solar system, increasingly distant from the Sun and from Earth, and increasingly difficult to observe with standard astronomical techniques. The object would continue to be observable for some time. The larger telescopes could follow it for years, but the period of intense daily observation by multiple facilities would gradually end. The flyby therefore marked, in many respects, the transition from the active observational phase of the object's transit to the more sustained, lower-intensity follow-up that would continue for as long as the object remained accessible. The images released by ESA captured the comet at this transitional moment, presenting one last clear visual record of the object before its slow recession into the outer solar system began in earnest. The release of the JUICE Janus images in early April 2026 had effects that went beyond their direct scientific content. The images were unusual in several respects that made them particularly impactful for the broader public discussion of 3I/Atlas. They were obtained from a position much closer to the comet than any Earth-based telescope could achieve. They showed the comet at a phase of activity that had not previously been documented in such detail. They came from a spacecraft that had not originally been part of the planned observation campaign for 3I/Atlas, but had happened to be in a fortunate position when the alignment occurred, and they were released to the public in a coordinated fashion that maximised their visibility in popular media. The images themselves showed 3I/Atlas as a bright, well-defined object surrounded by an extended cloud of gas and dust. The high-resolution imagery revealed structure within the coma that had not been clearly visible in the more distant Earth-based observations, including specific features near the nucleus that suggested complex activity patterns. The tail extended substantially in the antisolar direction, with structural details visible along its length. The overall appearance was that of an active comet visibly losing material to the surrounding space in the kind of detail that would not have been possible to obtain at any point in the comet's transit other than during this particular encounter. The release of the images was accompanied by the publication of the JIGNAS team's initial analyses, which interpreted the visible features in terms of standard cometary physics. The activity patterns were consistent with sublimation from specific regions of the nucleus, with some areas appearing more active than others. The dust grain size distribution could be inferred from the brightness profile of the coma. The temporal evolution observable across the Janus observation sequence provided information about how the activity varied as the comet rotated and moved through different geometric configurations. All of these analyses were standard cometary science applied to the unusual case of an interstellar object. What made the images particularly impactful was their timing in the broader narrative of the 3I/Atlas story. By April 2026, the initial wave of public interest in the object had largely passed. The discovery had occurred 9 months earlier, the perihelion passage 2 months earlier, and the various initial scientific papers had been published over the intervening period. The story had moved from the front pages of news coverage to the specialised scientific media, where it was being discussed in increasingly technical terms by a smaller audience of professional astronomers and serious amateur science enthusiasts. The release of the JUICE images, with their dramatic visual content and their evidence of an actively evolving object, brought the story back into broader public awareness at a time when many people had begun to forget about 3I/Atlas entirely. The renewed attention coincided with several other developments that contributed to the discussion. The Nature Astronomy paper on the deuterium ratio was published in late April 2026, providing new chemical evidence about the object's formation environment. Various additional papers describing other aspects of the chemical and physical characterization were appearing in scientific journals during the same period. The combination of new imagery and new scientific results produced a substantial body of new material for popular discussion, and the result was a kind of second wave of public interest in 3I/Atlas that brought many of the original questions back into active discussion. The lobe hypothesis, which had been substantially less prominent in public discussion after the initial coverage of the July 2025 paper, returned to attention during this period. Various commentators noted that the new images and the new chemical results added to the body of evidence about the object's unusual properties, and that the various unusual features taken together continued to support in their interpretation the possibility that the object was not simply a natural comet. Loeb himself was relatively quiet during this period, having said most of what he had to say in his original paper and in the subsequent statements that followed. But others took up the discussion, and the artificial origin hypothesis received renewed consideration in various venues. The mainstream scientific response continued to emphasize the natural origin interpretation. The new data in the mainstream view were broadly consistent with the picture of an unusual but natural comet from a different planetary system. The chemical anomalies could be accounted for by formation in a sufficiently different environment. The trajectory peculiarities could be explained by selection effects in detection. The lobe hypothesis was acknowledged as an interesting exercise, but was not considered to be supported by the available evidence at a level sufficient to displace the natural interpretation. The debate continued, but the mainstream consensus remained that 3I/Atlas was, with high probability, a natural object, extraordinary in its specific features but explicable through natural processes operating in environments different from our own. The various spacecraft in orbit around Mars provided observations of 3I/Atlas during a period when their position relative to the comet offered advantages over Earth-based observations. The closest approach to Mars, in October 2025, brought the comet within approximately 18 million miles of the planet, a distance that placed the comet within the effective observation range of the various Mars-orbiting instruments. The observations from these spacecraft constituted a significant component of the overall dataset accumulated during the comet's transit, and they provided perspectives that would not have been available from any Earth-based observation platform. The NASA spacecraft contributing to the Mars-based observations included the Mars Reconnaissance Orbiter, MAVEN, and the Perseverance rover on the surface of Mars. The Mars Reconnaissance Orbiter, in operation since 2006, carries the HiRISE camera among its instruments, one of the highest resolution cameras ever sent to another planet. The camera was used to obtain images of 3I/Atlas that, while limited by the substantial distance to the target, still provided meaningful spatial resolution. The resulting images contributed to the visual characterization of the comet during its transit through the inner solar system. MAVEN, the Mars Atmosphere and Volatile Evolution mission, has instruments designed primarily for studying the Martian upper atmosphere and its interaction with the solar wind. Some of these instruments could be repurposed for observations of 3B's I/Atlas. The ultraviolet spectrograph on MAVEN, for example, was used to observe the comet's emission in wavelength regions that complemented the observations from other facilities. The plasma instruments on MAVEN provided measurements of the local space environment that, during the close approach period, could detect the presence of comet-related material in the Martian vicinity. The Perseverance rover, operating on the surface of Mars, was used in an unusual mode for the comet observations. The rover's primary cameras and other instruments were designed for surface science, rather than for astronomical observation, but the cameras could be pointed upward to image the sky during periods when the comet would be visible from the rover's location. The resulting images were of relatively modest scientific value compared to those from the orbital instruments, but they had symbolic significance as the first images of an interstellar object obtained from the surface of another planet. The ESA spacecraft contributing to the Mars-based observations included Mars Express, in operation since 2003, and the ExoMars Trace Gas Orbiter, in operation since 2016. Mars Express has a suite of instruments including a high-resolution stereo camera that was used to obtain images of 3I/Atlas during the close approach period. The Trace Gas Orbiter has instruments designed for atmospheric science, but applicable in various ways to other observations. Both spacecraft contributed observations that complemented those from the NASA platforms. The scientific value of the Mars-based observations was substantial. The different viewing geometry from Mars provided perspectives on the comet that were not available from Earth, particularly during the period of solar conjunction when Earth-based observation was geometrically impossible. The different distance from the Sun meant that the comet appeared at different brightness and apparent size from Mars than from Earth, providing variations in observing conditions that could be used to refine the modelling of the comet's behaviour. The combined dataset from the multiple Mars-based platforms provided a coherent picture of the comet's behaviour during a critical phase of its transit. The observations also illustrated an aspect of modern space exploration that has become increasingly important: the ability to use spacecraft designed for one purpose to obtain observations that contribute to entirely different scientific objectives. The Mars orbiters had not been designed with the study of interstellar objects in mind. They were operating long after their original missions had nominally ended, conducting extended missions that took advantage of their continued capability to gather scientifically valuable data. When 3I/Atlas appeared, the operations teams for these spacecraft adapted their observation plans to include the new target, sacrificing some of the planned Mars observations in favour of the unprecedented opportunity to study an interstellar comet. The flexibility of modern spacecraft operations, the ability to respond to new scientific opportunities even when those opportunities were not part of the original mission design, was one of the unsung enabling factors in the broader observation campaign for 3I/Atlas. The contribution from Mars-based observations represented something new in the history of comet science. Previous comet observations had been made primarily from Earth or from Earth-orbiting spacecraft, with occasional specific missions designed to encounter specific target comets. The use of spacecraft at other locations in the solar system to conduct observations of an unexpected new target was relatively novel, and it pointed toward a future in which the network of spacecraft throughout the solar system could be used as a distributed observation platform for transient events. 3I/Atlas was the first interstellar object to benefit from this kind of distributed observation, and the experience with this object will probably inform planning for the next interstellar visitor when it eventually appears. NASA's Europa Clipper mission, launched in October 2024, was designed to study Jupiter's moon Europa, with particular attention to the subsurface ocean believed to lie beneath the moon's icy crust. The mission had a long transit phase between launch and arrival at Jupiter, with the spacecraft following a trajectory that included gravity assists from Mars and Earth, before its eventual arrival in the Jovian system. During this transit phase, the spacecraft was passing through interplanetary space and was equipped with instruments that could measure the local environment: magnetic fields, plasma, energetic particles, dust grains. These instruments were primarily intended to characterize the environments around Europa when the spacecraft arrived at its destination, but they could also be used to study other features of the space environment during the transit phase. In the autumn of 2025, the trajectory of Europa Clipper was calculated to pass through the ion tail of 3I/Atlas during a specific period from approximately October 30th to November 6th, 2025. The ion tail of a comet consists of charged particles that have been emitted from the comet's nucleus, ionized by ultraviolet radiation from the sun, and then carried outward by the solar wind. The ions follow the local magnetic field lines and form an extended structure that can stretch for tens or hundreds of millions of miles. The width of the tail at any given point is generally much smaller than its length, and the density of ions decreases rapidly with distance from the nucleus. But the tail is large enough that a spacecraft can pass through it if the trajectory geometry is appropriate, and the various ion and field measurements available on a spacecraft can characterize the material being encountered. The Europa Clipper mission team recognized the upcoming tail crossing and modified the planned operations to maximize the scientific return from the encounter. These spacecraft's instruments were configured to operate continuously during the relevant period, capturing the variations in local conditions as the spacecraft moved through and beyond the tail. The data were recorded on board and transmitted to Earth over the days that followed, with the analysis being conducted by the various instrument teams in subsequent weeks. What the observations revealed was a clear signature of the comet's ion tail. The magnetic field measurements showed disturbances consistent with the presence of additional ionized material in the local environment, draped around the magnetic field lines in the characteristic pattern produced by comet-solar wind interactions. The plasma measurements detected variations in ion density and composition consistent with the presence of comet-derived ions. The energetic particle measurements detected variations in the local particle flux that could be attributed to the disturbance caused by the comet's presence. The combined dataset provided the first direct in situ characterization of an interstellar comet's ion tail. The scientific implications of the measurements were significant. The detailed composition of the ions in the tail could be inferred from the instrument data, providing chemical information that complemented the remote spectroscopic observations from telescopes. The magnetic field structure could be analyzed to extract information about how the solar wind interacts with comet material, providing insights into the physics of comet-solar wind coupling. The variations along the trajectory through the tail provided information about the spatial structure of the tail and how it varied at different distances from the nucleus. Each of these analyses contributed pieces to the overall picture of the comet's physical and chemical properties. The Europa Clipper observations were also significant in a more general sense. They represented the first time a spacecraft had directly sampled material from an interstellar object. The Oumuamua encounter in 2017 had been entirely remote. No spacecraft had been positioned to encounter the object directly. The 2I/Borisov encounter in 2019 had also been entirely remote. The Europa Clipper encounter with 3I/Atlas's ion tail was therefore the first instance of in situ measurement of any material that had originated outside our solar system. The implications extended beyond the specific science of 3I/Atlas to the broader question of how the population of interstellar objects might be studied in the future. If specific interstellar objects could be targeted by dedicated missions, or if existing missions could be coordinated to pass through ion tails, as Europa Clipper did, then much more detailed information could be obtained than would be possible through remote observation alone. The data from the Europa Clipper observations were published in several papers during 2026, with detailed analyses of the magnetic field structure, the ion composition, and the particle dynamics. The papers contributed to the developing picture of 3I/Atlas, and also to the broader development of interstellar object science as a recognised subfield within planetary science. The Europa-Clipper team had not been planning to make contributions to interstellar object research when the mission was designed, but the fortunate alignment of trajectory and timing produced one of the most distinctive contributions to the 3I/Atlas science program. The experience suggests that future spacecraft missions might be designed with deliberate attention to opportunities for similar encounters with future interstellar objects, expanding the available toolkit for studying these rare visitors. The mainstream astronomical community's response to the Loeb hypothesis about 3I/Atlas was, on balance, skeptical. The reasons for this skepticism were various, and were articulated in numerous responses to the original Loeb paper, in commentary by other astronomers, and in subsequent scientific publications addressing the various features of 3I/Atlas that Loeb had cited as evidence for artificial origin. The skepticism was not uniform, and different astronomers focused on different aspects of the argument, but the overall pattern was that the mainstream community considered the natural origin interpretation substantially more probable than the artificial origin alternative, even after accounting for the various unusual features of the object. The most common criticism involved the statistical arguments in the Loeb paper. The probability calculations that produced the conclusion that the trajectory and other features of 3A/Atlas were improbable depended on various assumptions about the population of natural interstellar objects and about how that population would be expected to manifest in observations. Critics argued that these assumptions were uncertain, that small changes in the assumptions could substantially change the calculated probabilities, and that the specific assumptions used in the Loeb paper tended systematically toward making the natural interpretation appear less probable than it actually was. The criticism was that the statistical arguments were not robust, that they depended on parameter choices that could not be independently justified, and that produced different conclusions under different reasonable choices. A second common criticism involved the selection effects in detection. The Atlas survey that discovered 3I/Atlas, and similar surveys that constituted the major detection capability of the era, were specifically designed to detect certain kinds of objects, particularly objects on trajectories that might bring them close to Earth, with certain brightness characteristics in certain regions of the sky. Objects with these characteristics would be preferentially detected. Objects without them would be missed. The interstellar objects that have been confirmed represent a heavily biased sample of the underlying population, and the apparent unusualness of any specific detected object cannot be assessed without accounting for the selection effects. Critics argued that the Loeb paper had not adequately accounted for these effects, and that the features cited as evidence for artificial origin were exactly the features that would be expected to be overrepresented in a biased detection sample of natural objects. A third criticism involved the chemistry. The unusual chemical features of 3I/Atlas, the high CO2, the high deuterium, the various other peculiarities, were unusual relative to solar system comets, but not unprecedented relative to the broader range of chemical environments that occur in protoplanetary disks and other astrophysical contexts. Each of the unusual features could be accounted for by specific natural processes operating in environments different from those that produced our own solar system, and the combination of features could be accounted for by an object having formed in a single, specific kind of environment that happened to combine these various characteristics. The chemistry was strange but explicable. Critics argued that the Loeb paper underestimated the range of natural chemical environments and the consequent range of chemical features that natural interstellar objects might display. A fourth criticism, more philosophical than technical, involved the standards of evidence required to accept extraordinary hypotheses. Carl Sagan famously articulated the principle that extraordinary claims require extraordinary evidence. The proposal that 3I/Atlas was an extraterrestrial artifact was an extraordinary claim. It would, if accepted, represent one of the most consequential findings in the history of science. The standards of evidence required to accept such a claim should be correspondingly high. Critics argued that the evidence presented in the Loeb paper, while suggestive in various respects, fell far short of the extraordinary standard that the extraordinary conclusion would require. The natural origin interpretation, in this view, should be retained as the default position, not because it had been positively proven, but because the alternative had not been demonstrated with sufficient force. A fifth criticism involved the specific testable predictions of the artificial origin hypothesis. The Loeb paper had suggested that certain observations could in principle distinguish between natural and artificial interpretations of 3I/Atlas. The observations that became available during the subsequent months of the object's transit did not, in the mainstream interpretation, provide clear evidence in favour of the artificial interpretation. The chemical analyses showed natural cometary chemistry, even if unusual. The imagery showed a natural cometary structure, even if interesting. The various in situ measurements showed natural cometary behaviour, even if distinctive. Each new observation by this view added to the case for the natural interpretation by failing to produce the kinds of definitive evidence that would have been required to support the artificial interpretation. The cumulative effect of these criticisms was a mainstream view that 3I/Atlas was, with high probability, a natural object whose specific properties reflected the diversity of conditions under which planetary systems form throughout the galaxy. The object was scientifically valuable not because it was artificial, but because it was natural in unusual ways, providing direct chemical and physical access to material formed under conditions different from those of the early solar system. The Loeb paper and subsequent discussions identified various specific tests that could, in principle, have distinguished between natural and artificial interpretations of 3I/Atlas. The tests involved measurements that would have produced different results depending on whether the object was a natural comma or an artificial construct. Some of these tests were straightforward and were conducted as part of the standard observation campaign. Others were more difficult and required specific capabilities that not all observation platforms possessed. The aggregate result of these tests, as the observation campaign proceeded through 2025 and 2026, was generally interpreted as supporting the natural interpretation, but some specific features of the results remained subjects of continuing discussion. One category of test involved the physical properties of the object's surface and surrounding material. A natural comet should show specific patterns of surface composition reflecting the formation environment, with dust grains of certain sizes and compositions, ices of certain types, and a surface structure consistent with billions of years of exposure to interstellar conditions. An artificial object, by contrast, might show different surface properties, perhaps unusual reflectivity, perhaps specific materials not found in natural cometary populations, perhaps geometric features inconsistent with random natural processes. The spectroscopic and imaging observations of 3I/Atlas were used to characterize the surface and the surrounding dust and gas, and the results were generally consistent with natural cometary composition. The dust grains were of typical sizes for cometary dust. The ices showed standard cometary species. The surface, to the extent it could be characterized through indirect means, appeared consistent with natural processes. A second category of test involved the dynamical behavior of the object. A natural comet on a hyperbolic trajectory would follow that trajectory under the combined influences of gravity from the Sun and planets and the relatively small non-gravitational forces produced by gas emission from the nucleus. The actual trajectory could be calculated from these influences with high precision, and the observed trajectory could be compared to the predicted one. Any significant deviation from the predicted trajectory would indicate the presence of additional forces, perhaps the result of artificial propulsion, perhaps reflecting unknown physics. The trajectory of 3I/Atlas was tracked with high precision through the entire transit, and the observed trajectory matched the predicted natural trajectory to the precision of the measurements. The non-gravitational accelerations were consistent with natural cometary outgassing. No evidence of unexplained propulsion or other anomalous forces was detected. A third category of test involved the spectral and other electromagnetic signatures of the object. A natural comet should emit in specific wavelength patterns determined by the chemistry of the materials being released and by standard thermal emission processes. An artificial object might emit in different patterns, perhaps showing radio signals at specific frequencies, perhaps having unusual thermal characteristics that could not be accounted for by natural processes, perhaps producing specific spectral features inconsistent with any natural composition. Various searches were conducted for radio emissions, unusual thermal patterns, or other electromagnetic signatures that might indicate artificial origin. The results were consistently negative. 3I/Atlas emitted in patterns consistent with natural cometary processes, with no evidence of artificial signals or anomalous emission. A fourth category of test involved the directional behavior of the object. A natural comet should not show any consistent orientation relative to specific external features. Its rotation axis should be set by the conditions of its formation and subsequent evolution. with no relationship to features of the local environment in our solar system. An artificial object might show different behavior, perhaps maintaining a specific orientation relative to Earth, perhaps showing rotational patterns that suggested deliberate control. The rotational behavior of 3I/Atlas was inferred from observed brightness variations, and the resulting characterization was consistent with natural cometary rotation. No evidence of controlled orientation was detected. The aggregate result of these and other tests was a body of evidence that consistently supported the natural interpretation. Each individual test, taken alone, could not definitively rule out the artificial interpretation. There might be some specific kind of artificial object whose properties would mimic those of a natural comet closely enough to pass any specific test. But the combination of negative results across multiple independent tests made the artificial interpretation increasingly difficult to maintain. The mainstream conclusion, which crystallized over the months of the observation campaign, was that 3I/Atlas was, with high probability, exactly what it appeared to be: a natural interstellar comet, unusual in its specific features but explicable through natural processes. The artificial origin proponents, including Loeb himself, generally acknowledged that the available evidence was not decisive in favor of their hypothesis. The position they continued to maintain was not that 3/Atlas was definitely artificial, but that the possibility could not be definitively ruled out and that the question deserved continued serious consideration. The natural interpretation was the more probable conclusion based on available evidence, but the lower probability of the alternative did not justify treating it as impossible. The discussion would continue in various venues, but the active observation campaign for 3I/Atlas gradually transitioned from intense ongoing investigation to longer-term analysis of the accumulated data. The cumulative results of the various scientific tests applied to 3I/Atlas produced a coherent and detailed picture of the object that, while strange in many specific respects, was consistent with the broad category of natural interstellar comet, rather than with any alternative category that had been proposed. The picture is worth reviewing in its specific features, because the details matter for understanding what we have actually learned from the observation campaign and what we have not. The size of the nucleus was constrained to a range of approximately 440 meters to 5.6 kilometers, with the central estimates favoring values in the lower portion of this range when the reflectivity was assumed to be relatively high. The actual size remains uncertain but is probably in the range of 1 to 3 kilometers, making the object somewhat larger than 2A/Borisov, but not extraordinarily so. The size is consistent with the natural population of interstellar objects under reasonable assumptions about the underlying size distribution. The trajectory was characterized with high precision, with the orbital elements constrained to better than 1% on the major parameters. The eccentricity of approximately 6.3 firmly established the interstellar nature of the orbit. The path through the inner solar system was determined by gravity alone, with non-gravitational forces consistent with natural cometary outgassing. No evidence of any anomalous trajectory features was found. The composition was characterized through extensive spectroscopic observations from multiple facilities. The dominant species in the coma were water, carbon dioxide, and carbon monoxide, with various minor species including various organic compounds. The CO2 to water ratio of approximately 1.4 was unusually high compared to solar system comets, but consistent with formation near the CO2 snowline in a relatively cold protoplanetary disk environment. The deuterium to hydrogen ratio of approximately 30 times the typical solar system value was extraordinary, indicating formation in conditions substantially colder than those of the early solar system. The overall chemical signature was consistent with natural cometary composition from an unusual but plausible formation environment. The dust properties were characterized through imaging and through analysis of the brightness profile of the coma. The dust grain showed size distributions and optical properties consistent with natural cometary dust. The grain sizes ranged from submicron to perhaps millimeter scales, with the distribution similar to that found in active solar system comets. The dust composition, inferred from the optical and infrared properties, was consistent with the general categories of cometary dust, including silicates, organics, and various icy materials. The activity pattern was characterized through extensive observations across the entire transit. The activity began at distances substantially greater than the water snowline, driven initially by CO2 sublimation. As the object approached the Sun, water sublimation became increasingly important. and the activity intensified through perihelion before declining as the object moved outward again. The activity pattern was consistent with what would be expected for a comet of the composition and structure that the various observations had inferred. The rotation was characterized through analysis of brightness variations across the transit period. The nucleus appeared to rotate with a period of approximately several hours, similar to typical solar system comets. The rotation axis was determined to a moderate precision and showed no anomalous orientation features. The rotation was consistent with natural origin. The kinematic age, inferred from the high peculiar velocity and from kinematic models of the local interstellar population, was approximately 7 to 9 billion years. The age estimate is uncertain, but consistently places the object as older than the solar system, probably substantially older. The age implies formation in some now vanished planetary system around a star that has long since evolved past the planetary system stage. The aggregate picture is of an object that is natural in its physical and chemical properties, that originated in a planetary system substantially different from our own, that has been wandering through the galaxy for billions of years, and that happened to encounter our solar system during a brief moment in its long journey. The object is unusual in specific respects compared to the comets of our own solar system, but the unusualness reflects the diversity of natural environments in which planetary systems form, rather than any departure from natural processes. The features that Loeb and others had cited as potentially indicating artificial origin were generally accounted for by the natural interpretation, though not always to the satisfaction of all observers. What the test showed, in summary, was that 3I/Atlas is exactly what the standard astronomical framework predicted that interstellar objects could be: messengers from elsewhere, carrying the chemical and physical signatures of their distant origins, providing direct access to the conditions that prevail in other planetary systems. The artificial origin hypothesis remained available as a possibility that the available evidence could not entirely rule out, but the positive evidence for the natural interpretation was strong enough that the artificial alternative was not the most reasonable conclusion to draw from the data. The discussion would continue, but the observational basis for evaluating it would be increasingly stable as the active observation campaign concluded and the longer-term analysis of the accumulated data proceeded. By the spring of 2026, 3I/Atlas was moving outward from the inner solar system on its long journey back into interstellar space. The perihelion in February had marked the closest approach to the Sun. The Jupiter flyby in March had been the last major planetary encounter. After these events, the object's trajectory carried it outward, past the orbits of the outer planets, through the trans-Neptunian region, and eventually into the open spaces beyond the solar system's boundary. The departure was less dramatic than the arrival had been. There would be no specific event marking the moment of departure, no clear boundary that the object would cross, but the gradual recession would carry 3I/Atlas out of meaningful observational range over a period of years. The specific trajectory parameters allowed the future path to be calculated with substantial precision. 3I/Atlas would continue moving outward at approximately 130,000 miles per hour relative to the Sun, gradually decelerating as the gravitational attraction of the Sun continued to act on it. The deceleration would be modest at the distances involved, however, and the object would retain a substantial fraction of its initial velocity, even after it had moved well beyond the major planets. The asymptotic velocity, the velocity it would have once it was so far from the Sun that the Sun's gravity no longer significantly affected its motion, would be approximately 36 miles per second, identical in magnitude to the velocity at which it had originally entered the solar system. The path would carry 3R/Atlas in a specific direction determined by the geometry of its hyperbolic orbit. The outgoing direction was not the same as the incoming direction. The Sun's gravity had defected the object's path during its close approach, bending the trajectory by a specific angle that depended on the orbital eccentricity and the closest approach distance. The outgoing direction would carry the object toward a specific region of the sky, which could be calculated from the orbital elements. The specific direction does not point toward any particular star or stellar system that 3I/Atlas might encounter. Interstellar space is too vast, and the probability of a close encounter with any specific star is too small to make such predictions meaningful. The object would simply continue moving through interstellar space, drifting through the galaxy for billions of years, until perhaps it encountered another star at some point in the indefinitely distant future. The expected departure from the solar system, in the sense of moving beyond the region where the Sun's gravity dominates the dynamics, would occur over a period of decades. The boundary of the solar system is not sharply defined. Gravitational influence falls off gradually with distance, and the transition from inside the solar system to in interstellar space happens continuously rather than at a specific moment. By common convention, the boundary is sometimes placed at the heliopause, where the sun's particle outflow gives way to the interstellar medium, or at the outer edge of the hypothesized Oort cloud, where the sun's gravitational influence becomes weaker than the influences of nearby stars. By either definition, 3I/Atlas would cross the boundary some decades after its arrival, by which time it would be too distant to observe even with the largest telescopes. The current expectation among the scientists who study 3I/Atlas is that the object will remain observable in principle for some years, becoming progressively fainter and more difficult to observe as it recedes. Specific large telescopes will continue to monitor it as long as the science return justifies the observing time investment. The data accumulated during the active transit phase will continue to be analysed for years, with the various measurements providing the basis for many additional scientific papers as different research teams extract specific results. The active observation campaign has effectively ended, but the scientific study of the object will continue indefinitely as the accumulated data are analysed and reanalysed by future researchers. What will remain after the active observation phase has ended and the object has receded beyond observability is the body of knowledge that has been built through the months of intense study. The chemical analyses, the physical characterizations, the trajectory measurements, the various other scientific products. All of these will continue to exist in the scientific literature and the data archives available to researchers for as long as those archives are maintained. The object itself will continue on its journey through the galaxy, but our knowledge of it will be fixed at the level of detail that was achievable during the brief window of observation. Future interstellar objects will be studied in their own contexts, and the methods and frameworks developed during the 3I/Atlas study will be applied to them, but 3I/Atlas itself will pass into history as the third confirmed interstellar visitor, the largest and most chemically distinct of the three, and the one whose specific features produced the most extensive scientific and public discussion in the brief period during which it was accessible to study. The discovery and characterization of 3I/Atlas, taken together with the earlier discoveries of Oumuamua and 2I/Borisov, has established that interstellar objects pass through the inner solar system at rates substantially higher than had been suspected before the era of systematic detection began. The implication is that the broader population of interstellar objects in the galaxy is correspondingly large, and that many more such objects could be detected if appropriate observational capabilities were deployed. The recognition of this larger population has consequences for how future interstellar object discoveries can be expected to proceed, and for how the resulting science can be designed to take maximum advantage of the opportunities. The most direct consequence is that the search for interstellar objects has become a recognized subfield of astronomical research with dedicated planning and resource allocation. Before 2017, interstellar objects were a hypothetical category whose actual existence had not been confirmed. After the discoveries of Oumuamua, Borisov, and Atlas, interstellar objects became an empirical category whose properties could be studied through repeated observation. The transition from hypothetical to empirical changed the nature of the subfield, and the funding, infrastructure, and scientific attention devoted to it have expanded substantially. The most important upcoming development is the Vera C. Rubin Observatory in Chile, which began its main scientific operations in 2025 and which is expected to dramatically increase the rate at which interstellar objects are detected. The Rubin Observatory's Legacy Survey of Space and Time, abbreviated LSST, will survey the entire visible sky every few nights with sensitivity substantially greater than any previous survey. The increased sensitivity and coverage are expected to detect interstellar objects at rates of several per year, possibly more, providing many more opportunities for scientific study than the previous detection rate of approximately one every few years. The Rubin Observatory was, in fact, already operating during the discovery and early observation period of 3I/Atlas, and it contributed to the observation campaign. The observatory's LSST cam captured images of 3I/Atlas during science validation observations conducted in mid-2025, providing some of the highest quality imagery obtained for the object during its initial discovery period. The observatory's full operational program is expected to substantially expand the inventory of detected interstellar objects in the years ahead, with each new detection providing additional information about the population as a whole, The implications for scientific strategy are substantial. With multiple interstellar objects available for study each year, it will become possible to characterize the population statistically, rather than just the individual objects. The size distribution, chemical diversity, kinematic properties, and other features of the population can be estimated from accumulating samples, and the implications for galactic structure and chemical evolution can be developed in ways that were not possible when only one or two objects had been studied. The scientific value of any specific future interstellar object will derive in part from the contribution it makes to this broader population characterization, in addition to whatever specific scientific results emerge from its individual study. The implications for planning future dedicated missions are also significant. The European Space Agency's Comet Interceptor mission, scheduled for launch in approximately 2029, is specifically designed to encounter a previously unknown comet, possibly an interstellar object, by being held in a stable parking orbit until a suitable target is identified. The mission will then maneuver to encounter the target, providing the first close-range study of an interstellar object if the target proves to be one. The mission concept emerged in part from the realization that interstellar objects appear in the inner solar system unpredictably, and that any dedicated mission to study them must be flexible enough to respond to discoveries as they occur. The increased detection rate expected from the Rubin Observatory will increase the probability that Comet Interceptor will have a suitable interstellar target during its operational lifetime. The implications for theory are perhaps the most fundamental. The detection of 3 interstellar objects with substantially different properties, Oumuamua strange features, Borisov's relatively ordinary comet behavior, Atlas's chemical peculiarities, suggests that the population of interstellar objects is diverse rather than homogeneous. Each object carries information about the specific planetary system in which it originated, and the diversity reflects the diversity of planetary systems throughout the galaxy. As the population of detected objects grows, the resulting picture of galactic chemistry, planetary formation, and the broader dynamics of small body populations will become substantially richer than it currently is. The era of interstellar object science is, in this sense, just beginning. The discoveries through 2025 have established that the objects exist, that they can be detected with current technology, and that they carry scientifically valuable information. The discoveries to come over the years and decades ahead will progressively fill in the picture, characterizing the population in detail and using the information to address questions about planetary system formation and galactic structure that have been difficult to approach through other means. 3I/Atlas will be remembered as one of the founding objects of this new field, contributing both to the specific scientific results that emerged from its study and to the broader development of the methods and frameworks that the field has begun to establish. The scientific study of 3I/Atlas has produced a substantial body of information about a specific object that briefly passed through our solar system. We know approximately where the object came from in general terms, an old, cold region of the galaxy, perhaps the inner regions where stars are denser and chemical evolution has produced different conditions than those of our local neighborhood. We know approximately when it formed, billions of years ago, in some now vanished planetary system around some long-dead star. We know its composition in considerable detail: water with unusual isotopic ratios, substantial amounts of carbon dioxide, various organic compounds, dust grains of typical cometary types. We know its size to within roughly an order of magnitude, its rotation period to within reasonable precision, its trajectory to high accuracy. We know it is leaving our solar system and will continue moving outward through the galaxy for billions of years to come. What we do not know, and what the available evidence does not allow us to determine with certainty, is what 3I/Atlas actually was in some deeper sense. The natural origin interpretation accounts for the observed features adequately, but it does so by appealing to specific formation conditions that we cannot directly verify and that may not be uniquely determined. The artificial origin interpretation accounts for the observed features less satisfactorily, but cannot be definitively ruled out by the available evidence. The probability that the object was natural is substantially higher than the probability that it was artificial, but both remain possibilities in some meaningful sense, and the available evidence does not collapse the distinction entirely. The question at the level of definitive proof remains open. This kind of open question is, in some respects, characteristic of how science actually proceeds. Most scientific knowledge is provisional rather than absolute, supported by evidence that makes certain conclusions more probable than others, without ever achieving the kind of absolute certainty that mathematics or pure logic might provide. The natural origin interpretation of 3I/Atlas is, by reasonable scientific standards, the conclusion that the available evidence supports. The artificial origin alternative is, by the same standards, a possibility that the evidence has not definitively eliminated, but that the evidence does not specifically support either. The state of the question reflects the state of available evidence, and the state of available evidence reflects what we have been able to learn about the object during the brief period when it was accessible to study. What the question reveals, perhaps more clearly than the answers would have, is the fundamental nature of our situation in the universe. We are observers in a vast environment whose features we can study only when those features happen to come close enough to our location to be observable. The features that do come close, like 3I/Atlas, provide brief opportunities for study that can produce substantial information, but can rarely produce complete information. The features that do not come close remain inaccessible, regardless of how interesting they might be. The picture of the universe that we have been able to construct through this process is necessarily fragmentary, with our knowledge concentrated in the regions and the timescales we have been able to access and absent everywhere else. 3I/Atlas came close. We studied it as thoroughly as we could during the months of its transit. We learned what we could learn within the constraints of what was observable, and then it moved on, continuing its journey through the galaxy, taking with it whatever additional information remained inaccessible to our observations. The question of what 3I/Atlas actually was, beyond what we measured about it, will probably never be definitively answered. The answer is now beyond our reach, travelling through interstellar space at 36 miles per second, growing more distant with each passing day. The next interstellar object to be discovered may be very different, perhaps a typical comet that adds little to what we already know, perhaps something we cannot yet imagine. What 3I/Atlas leaves behind is not a final answer, but a richer set of questions. The galaxy is filled with objects we have not yet seen, in environments we have not yet characterized, around stars whose planetary systems have not yet been studied. Some of these objects will eventually find their way to our solar system, and we will study them when they do. The story that 3I/Atlas began is, in this sense, only the beginning of a much longer story about how the galaxy is structured and what kinds of things have happened in it across the billions of years of its history. The question that we still cannot answer is whether any of these things were ever made by anyone. We have not seen evidence that they were. We have not seen evidence that they were not. The question remains, as it has remained for as long as humans have considered it, fundamentally open. We continue to watch the sky.